So my screen is visible?
Yes.
Yes, ma'am.
Okay, thank you. Hello? Am I audible?
Yes, ma'am.
Yeah. So, good afternoon to all of you. So today I will be talking on dialogue systems. So I am already taken a course on information extraction. So I am Dr. Sriparna Saha. So I am currently associate professor in the Department of Computer Science and Engineering, IIT Patna, and I am also associate in research and development of IIT Patna. So this is my web page. So, and this is my email addresses, sriparna@iitb.ac.in and sriparna.saha@gmail.com. So if you have any questions regarding any any portions of the talk, you can email me, or you can also visit my web page to get the recent publications. So today my talk is having several components. So first I will discuss the what do we mean by dialogue, what do we mean by dialogue systems. Then the dialogue systems has many components like dialogue act classification, intent detection, slot filling, dialogue management strategies, and then we also have the sentiment aware multimodal dialogue policy learning. And finally, we will be discussing about the natural language generation. So these are the different components of dialogue systems. So I will be discussing about all these things. So basically, what is a dialogue? So you know that dialogue systems means there is an agent, and the agent is talking with the computer. So like agent is talking, hello, how can I help you? The agent is saying my computer is not working. Then the agent is keep on talking with the customer, and the agent's in basically intention is to understand what is the problem faced by the customer, and accordingly the agent has to basically gather the information from the customer and finally create that solve my problem. So that way basically this is there is a agent and there is a customer, and the conversation is going on between the agent and the customer. So this is mean by a dialogue systems. We need to basically design the agent which can basically chat with the customer. So this agent is a computer agent. So this is an automated agent. So we need to somehow design such an agent which can easily talk with the customer. Oh, and then basically it should somehow try to gather information from the customer. So what is a dialogue definition? A formal discussion of a topic in speech or writing. So connected series of utterances, a text or conversation. So basically dialogue is a formal discussion of a topic in speech or writing. It is a connected series of utterances, a text or conversation. This is the exchange of ideas or opinions on a particular issue with a view to reaching an amicable agreement. So this is the exchange of ideas or opinions on a particular issue with a view to reaching an amicable agreement. So basically dialogue is a connected series of utterances, a text or a conversation. It is an exchange of ideas or opinions on a particular issue with a view to reaching an amicable agreement. So there are several characteristics of a dialogue, like whose turn it is. So who will now say whether the agent will tell, or whether the agent will say or the customer will say. So whose turn it is, what are the intentions of the dialogues, how to reply back. So there are several characteristics of a dialogue, whose turn it is, whether it is the agent's turn or whether it is the customer's turn, what are the intentions of a particular dialogue, and how to reply back. So these are the different characteristics of a dialogue. The dialogue system is basically this is the picture of a dialogue system. So there is a user input like which restaurant can I book for 2 people for today. So given the user input, there is a natural language understanding module. So the natural language understanding module is responsible for understanding the type of the dialogue. Like which restaurant can I book for 2 people for today? So we need to apply a natural language understanding module, and natural language understanding module has to basically find out the dialogue act. So whether this is a question or this is a statement or this is a greeting or this is a open question. So that is the task of the dialogue act classification, to understand what is the type of a particular dialogue. For example, which restaurant can I book for 2 people for today? This is a question. Okay, so the dialogue act classification will provide the answer question as a dialogue act. Then the second is basically the intent classification. So basically intent classification means to understand the intent of a user. So which restaurant can I book for 2 people for today? So here the intent is it wants to book the restaurant. So basically the second task is to understand the intent of a particular dialogue. And the third is the slot filling. So like here, the slots are basically the person want to book for 2 people and for today. So there are some important slots, like the person want to book the restaurant for 2 people and also for today. So basically these are the slots. So basically this is the state, like there is a finally this slot module will provide the information. It will extract information from the user utterance, and then there will be a state. The state is having information like date equal to today and number of people equal to 2. And this state will be given as an input to the dialogue manager. And the dialogue manager is basically responsible for picking up an action. So dialogue manager will be responsible for picking up an action of ask. So basically now the user agent will ask some additional questions. Okay. So the action, depending on the state, some action will be picked up, that is by the dialogue manager, and this action will be translated into system response by the natural language generation module. So the natural language generation module will basically translate the action into system response. So basically this is the whole dialogue system. So basically the user is asking for a question. Then there is a natural language understanding module. So the natural language understanding module is, there are 3 components of natural language understanding module: dialogue act classification, intent classification, and the slot filling. So dialogue act classification is for classifying the dialogue acts. Then intent is for predicting the intent of a particular dialogue. And the slot filling is for identifying the information from a particular utterance. So then the dialogue manager is responsible for translating the state into action. So it will basically translate the state information into an action, and the action will be translated into system response by the natural language generation module. So this is the whole dialogue system. So now the dialogue act classification. So dialogue act classification. So now I will discuss about different components of a dialogue systems. As I mentioned that already I have mentioned, this is the overall picture of a dialogue system. So dialogue system is having several components like dialogue act classification, intent classification, slot filling, dialogue manager, natural language generation, all these. So I will be discussing about all individual components. So dialogue act classification, so to identify the communicative intention of a speaker in a dialogue conversation, which is classified into a predefined category. To identify the communicative intention of a speaker in a dialogue conversation, classified into a predefined category. So basically, you know that what kind of experience do you have then with the child care. So this is a type of a question. Then how about you? This is an open question. That's all right. This is an understanding. So basically, to identify the communicative intention of a speaker in dialogue conversation is basically going to classify into a predefined category is basically called a dialogue act classification. To understand the type of a particular dialogue. So whether the particular dialogue is a question, or it is an open question, or it is a statement, or it is an understanding. So that has to be understood by the dialogue act classification. So there are several works in the dialogue act classification. So there is a data set available which is called the SWBD. It is an informal corpus of human-human interactions. So it consists of 1,155 dialogue conversations amounting to more than 2 lakh utterances. So this HWBD DAMSL tax set comprises of 42 categories of dialogue acts. So this tax set is having 42 categories of dialogue acts. Then there is a data set which is called the trends. It is a task-oriented corpus where a user collaborates with a planning assistant to accomplish some task involving manufacturing and shipping goods in a railroad freight system. So it comprises of 98 dialogue amounting to about 7,000 utterances. So basically, this is the data sets used. So in the first part, I will show you some work which are recently done by us. So I will show you how there's some machine learning or deep learning based techniques can be applied to solve the dialogue act classification problem. So the first work will show you some machine learning and deep learning based techniques for solving the dialogue act classification problem. So as the SWBT DAMSL taxset has 5 categories, so it is not very useful for restricted domain applications. So we have proposed a new possible taxonomy that can divide the utterances into more generic classes. So it is flexible for modeling a chatbot. So basically, the original dataset taxset is having 500 categories, which is not very useful for restricted domain applications. So we propose a new possible taxonomy that can divide the utterances into some generic classes. So basically, we proposed a new taxonomy where there are some less number of classes. So in our proposed taxset, there are some possible classes like question, acknowledge, greeting general, statement, comment, etc. So basically, in our case, there are only 5 classes: question, acknowledge, greeting general, statement, and the comment. These are the 5 classes which are available in the taxonomy. So these are the descriptions of these 5 classes. So question means contains utterances that represents any type of the questions. Like who is Chris Manning? So this is a type of a question. Greeting general involves greetings, goodbyes, and basic small talks showing expression of gratitude toward listener. Like good morning, good afternoon. So all these are basically greetings. Then there is an acknowledgement or CAT. But this involves explicit affirmations, disagreement, or confusion from the user side, as well as the instances that indicates end of the conversations. Like, yeah, okay. So these are the examples of the acknowledgement. Then comment, this involves asking the system to perform an action, which may include display, search, generate, etc. So like found the book. So this is a kind of a comment. This involves asking the system to perform an action which may include display, search, generate, etc. So like, for example, the pass the book. This is an example of a comment. Then there is a statement or information utterances that contains any piece of information that can be used to extract attributes. So he is Austria right now. So this is a statement of the information. So utterances that contain any piece of information that can be used to extract attributes. So he is in Austria right now. This is an example of a statement of the information. So this is the proposed taxonomy. In our proposed taxonomy, there are 5 types of tags mostly. So we have used the question, greeting general, acknowledgement, comment, and the statement. So these are the examples of a dialogue like, hello, how may I help you? This is the greeting general. Show me flights to Mumbai today. This is the comment. May I know the departure place? This is a question. Oh, it's Bengaluru. This is a statement. So you want to fly from Bengaluru to Mumbai. This is a question. Yes, this is the acknowledgement. The flights are GS 383 at 2 p.m. and IN 541 at 10:30 p.m. This is an example of a statement. Thank you for the information. This is again a greeting. So this is the overall architecture of. Yeah, hello.
I just have a doubt.
Yeah, please.
Ma'am, in the previous, yes ma'am, this slide, in the first sentence, hello, how may I help you? Like you have a question as well right now, ma'am. So how do you identify whether it's going to be a greeting or a question?
Oh, so this is the actually as this is starting with the hello. So
Okay.
we have given the more emphasis on hello because this is the
Okay.
past utterance. So the past utterance is basically given the it is tagged as the greeting because in the past utterance only it is a how may I help you. This is a kind of way of greeting only. So we have
Okay.
given emphasis on hello only.
Okay, ma'am.
Yeah, but you are correct. It could be also a question.
Okay, ma'am. Thank you.
So this is the overall architecture of the dialogue act classification. So we can yeah Anusha, you were asking some question. Anushka, you raised a hand. Anushka, are you there? Okay, so this is the overall architecture of the whole system. So there is a data set. We have to first reprocess the data set. Then there is a taxonomy preparation. As I mentioned that we have created these 5 categories of the 5 tags. So 5 different tags we have basically created. And that is basically called the taxonomy. Then there are these word vectors. So basically, that we have used several different features. So I will soon show you what are the features that we have used. So we annotated the data with the taxonomy. Then all the features are extracted. So by using some feature selection technique, we selected some base set of features. And those base set of features are given to the CRF module. And there is a dialogue act classification. And there is also an experiment where all the features without feature selection are given to the CRF module. And then there is a dialogue act classification. So basically, that after we are extracting several handcrafted features, and then from all the handcrafted features are given to the CRF. And in the another approach, we have selected a few subset of features, and then those features are given to the CRF. Okay, so there is a feature selection without feature selection. What is the effect? So methodology 1 is without feature selection, where all the handcrafted features are fed to the system. And methodology 2 is basically with feature selection, where all the features are basically extracted from the set, and then those are passed through the CRF layer. And then in the third approach, what we did, we apply some clustering technique on the word vectors. So there is a word to vec model. So we apply the clustering technique on the word vectors. We opted the we apply the word to vec model on the data, and we basically apply the clustering technique on the word vectors, and then the cluster numbers are used as the features. So basically, we have used the cluster numbers as the features, and that is basically passed to the CRF, and then the dialogue acts. So this is the methodology 1. So basically, our classifier is the conditional random field, which is a sequence leveling task. So it is a sequence leveler. So here the features are lemma form of the words, lemma bigrams, part of speech tags, and their bigrams, the speaker information. And the class specific features used to improve the performance of the target class. So there are some class specific features like for the question class, we have searched whether the sentence starts with what, where, when, which, who, how, and whether question mark is also there or not. So basically, we have searched whether the sentence starts with what, where, when, which, who, how, or there is a question mark at the end or not. Then there is a greeting general, so presence of sorry, thank you, hello, hi, etc. So basically, that for the greeting, we have searched for whether the sentence is having any hello, hi, sorry, or thank you, etc. Then for the cat class, we have searched for the words like who, okay, yes, no, who, etc. So these are all the handcrafted features. So these handcrafted features are extracted from the data, and then we pass through this conditional random field, which is a classifier. And it is a sequence leveling task because depending on the previous, the context plays a very important role. what would be the category of the current utterance, that will depend on the previous categories. So we did a ablation study to improve the accuracy and identify important and contributing features. So basically we did an ablation study, we improved the accuracy and identified the important and contributing features. Conducted in the forward direction, that is the features are combined one after the other. The difference in the accuracies is used as an estimate of the importance of the feature. So difference in the accuracies is used as an estimate of the importance of the feature. The best performing features are taken and rest of the features dropped to reduce the complexity. So difference in the accuracies is used as an estimate of the importance of the feature. The best performing features are taken and rest of the features are dropped to reduce the complexity. So in the method 2, we have used a, again a CRF classifier. So CRF is used for sequence leveling task. So we have used the word embeddings of the corresponding words and the best performing features obtained from the ablation study. So we did an ablation study of the features and we carefully selected few features which are important for our particular task, and those features are used for the classification purpose. So we use the word embeddings of the corresponding words and the best performing features obtained from the ablation study, and those features are basically used for the classification task. So the pre-trained Google News word embeddings of dimension 300 is basically used. In methodology 3, there is a sequence. Again, it is a sequence leveling task. Conditional random field is basically used as the classifier. So there are several features that are used. One is the word cluster IDs of the corresponding words. So we on the word vectors we applied the K-means algorithm, and K-means algorithm determines the clusters. Basically, it basically merges some words and keep them into a single cluster. So it somehow generates the clusters of the word vectors, and this cluster number is basically used. Cluster number is basically used as a feature value. The best performing features obtained from the ablation study: lemma, unigram, bigram, part of speech. So basically, all these features are used, and also the cluster ID is basically used as a feature. So we are not only using the original word vectors, but we are also using the best performing with the cluster ID. So we apply some K-means algorithm to cluster the word vectors, and then the cluster ID is basically used as an additional feature. So this is the thing that suppose there is a sentence like show me flights from Denver to Baltimore. So now all these words are having a vector. By using the word to vec model, you can easily get the word vectors of show, word vector of me, flights, Baltimore. So you can easily get the word vectors of all the individual words. Now you can basically have clusters. You can apply clustering, and then you can form clusters of these words, and the cluster ID, like here now we are not using the actual word vector, but we are using the cluster ID. Like show is having cluster ID G_3, me is having cluster ID G_29. So this way we are basically having several cluster IDs, and that is basically the feature vector. So I hope you understand that now we are not only using the word vectors, but we are somehow applying clustering on the word vectors, and then the cluster IDs are basically used as a feature. So these cluster IDs are used to represent the whole sentence. So in the methodology 4, we have used some deep learning based model, because recent years deep learning plays a very important role. Deep learning based techniques become very popular. So we have developed some deep learning based methods for solving this dialogue act classification problem. So there are two baselines: CNN with fixed filter size of 3 and CNN with multiple filters of size 3, 4, and 5. So to the baseline, variants of RNN such as LSTM were incorporated. So finally, features such as part of speech and cluster IDs were augmented with the system. So basically, we are using some deep learning based models, and to the baseline variants of RNN such as LSTM were incorporated. Finally, features such as part of speech and cluster IDs were augmented with the system. So we have incorporated the additional features like part of speech and the cluster IDs with the system. So this is our overall architecture. So basically, that word embedding, we have generated the word embedding, and also we have the part of speech and the clustered embedding as additional feature. So we're not only using the word embedding, but we are also using the corresponding part of speech information, and we are also grouping the words based on the word embeddings. Like I mentioned that here, all the words are clustered based on their vectors, and then the individual cluster is having an ID. So that ID is basically used to represent the word. So this way, basically, this is one additional feature. So like we have the word embeddings, plus we have part of speech and other cluster embeddings, and then all are concatenated together, and then we are passing through the RNN unit or the dense layer. Yes, any question? Hello? Yeah, so then we are concatenating these features together, and then we are passing through the RNN unit and the dense layer, and then there is the output. So these are the results of the methodology 1 and the ablation study. So all features, with the DAM SL tax set, we are getting 72.750 accuracy, 48% F score. And with our proposed tax set, because our proposed tax set is very having minimal number of tags. With our proposed tax set, we are getting say F1 score of 76%. And for our and these are the base features. So with after feature selection, if we do so, then for our proposed tax set, there is an improvement in the accuracy. So the base features are giving us some improvement in the accuracy. So feature selection is indeed required. When we are doing this word embeddings only, when you are using only the word embeddings, we are getting a F1 score of 71%. And when we are using word embeddings plus the base features, then we are getting an F1 score of 75%. So then cluster IDs. So only for the cluster IDs, we are getting 45.12%. Cluster IDs, but the base features are giving us 76.43%. These are the results of the deep learning based techniques. So deep learning based techniques are basically with the part of speech and with the cluster features, we are getting the maximum accuracy of 91.13%. So these are some error analysis. So like you can see that, can you tell me the way to Patna? So this is basically, originally it is a question, but our system is predicting as a comment, because can you has two literal meaning. Then I am going to Lucknow, book me a hotel there. So again here, the original is basically a comment, but we are getting this as an info. So utterances are not explicitly comment types. Okay, I will also come tomorrow morning. So here the original is basically information, but we are predicting this as a cat, CAT. Cat has much occurrence of words like okay, yeah, etc. No, it's not possible. So originally it is cat, but we are getting this as an information. So it is basically replying to a question. So now I will show you how basically in recent years, dialogue act classification can also be formulated as a multimodal classification problem. So in the last work, we have only used the text portion to predict the dialogue act. We have used the text portion, but the person's facial expressions, then the voice tones can also be used to predict the dialogue type. So basically in this particular work, we have used the multimodal approach. So we have not only utilized the text portion, but also the tone of the speaker and also the gaze features of the speaker to predict the dialogue acts. So this is the thing, primarily all the works in DSC limit themselves to utilizing only the textual modality. Non-verbal features, change of tone, facial expression, etc., can provide useful cues to identify DAs, thus stressing the role of incorporating multimodal inputs into the task. So basically in this particular task, we have utilized all the non-verbal features like change of tone, facial expression, etc. can provide useful cues to identify DAs, thus testing the role of incorporating multimodal inputs into the task. And also we have seen the emotional state of the speaker has a substantial effect on the pragmatic content. So the emotional state of the user can also help us in identifying the dialogue act. So for example, the utterances such as okay, sure, yeah, right can be considered as agreement or disagreement if implied sarcastically. Mostly in expressive DAs such as greeting, thanking, apologizing, etc., speaker emotion can assist in recognizing the communicative intent. So basically, the emotion and emotional state of a user can also help in identifying the dialogue acts of a particular utterance. So this is the thing that we proposed an attention-based self-intermodal, intertask, multitask, multimodal deep neural network for jointly optimizing the dialogue act classification and the emotion recognition. Emotion recognition has been treated as an auxiliary task, adding the primary task DSC. We curate a new dataset which is called the multimodal emotion DA, which is called the EMOTIDA, with high quality annotations of DAs, including emotionally aided cues for facilitating research in multimodal DSC and linked to a novel subtask which is called the emotion aware DSC. We established that multitasking and multimodality boosted the identification of DAs compared to its single task and unimodal DSC variations. So this is the EMOTIDA dataset. So first we scan through the literature for existing multimodal emotion recognition datasets. So we find out two datasets, the IIMA CAP and the MELD. These are the two popular datasets. And these datasets are not annotated for their corresponding dialogue acts. So these datasets are not having any dialogue acts. So basically, we already know that SWBD, DAMSL, this dataset is taxit is having 42 dialogue acts used as the basis for conceptualizing taxet for the EMOTIDA dataset. So 12 most commonly occurring tags were used to annotate utterances of the EMOTIDA dataset. So we selected 12 tags which are mostly popular, like greeting, question, answer, statement opinion, statement non-opinion, apology, comment, agreement, disagreement, acknowledge, back channel, and others. So these 12 tags are used as the final tag set. To remove the discrepancy in the number of emotion tags for IMOCAP and mail datasets, the joy tag of the mail dataset was mapped to happy tag of the IMOCAP to finally settle on 10 emotion tags from the IMOCAP for the EMOTIDA dataset. Conversations from IMOCAP and mail dataset were converted for the corresponding DA tags. So this is the EMOTIDA dataset. So finally, our proposed EMOTIDA dataset is having 1341 dyadic and multi-party conversations, resulting in a total of 19,365 utterances or annotated videos with emotion and DA tags. So each utterance contains three modalities: video, audio, and the text. So this is an example like adults don't snap, they sting. So here the dialogue act is basically DAG, or what is the full form of DAG? So basically DAG is the disagreement and the emotion is anger. Then I just checked on messages and Jesua didn't call. So this is a statement and the emotion is basically sad. So you can understand that each utterance is having now two tags. One is a dialogue act tag and that is the emotion tag. And each utterance is not only having the text component, but also having other modalities like video and the audio. So that is very amusing indeed. So here the dialogue act is basically again the disagreement and the emotion is basically anger. Come on, pick up, pick up. So here the dialogue act is basically a comment and the emotion is basically fear. So sample utterances for the EMOTIDA dataset with its corresponding DA and emotion categories. So you can see that in our EMOTIDA dataset, IMO cap is contributing 48% and male is contributing 52%. And these are the distribution, overall speaker distribution. So there are many speakers and their distribution is basically shown in this wheel. And this is also a distribution of the emotion levels and the distribution of dialogue act levels. So you can see that how the distributions vary. Like there are basically the emotions are neutral, sadness, anger, fear, happy, surprise, disgust, frustrated. And in the dialogue act, we have statement, question, answer, greeting, comment, agreement, disagreement, etc. There are many such 12 tags, and their distributions are shown in this particular figure. So basically, there are some qualitative aspects of the emotica. So emotion indeed helps in identifying the dialogue act. So why we are going to solve both the tasks together, emotion analysis and the dialogue act classification? Because the emotion recognition indeed helps to understand the dialogue act. So these examples illustrate the importance of having emotional information while deciding the dialogue act of an utterance. Like suppose there is an utterance, I can't leave it. You gauged a hole in my dingy floor. So here the emotion is anger, and that can help us to understand that the dialogue act is basically disagreement. Well, you know, I appreciate you coming over and talking to me. I mean, it definitely helps. So here the dialogue act is basically acknowledge and the emotion is sad. So the sad basically helps that it is a type of dialogue act equal to acknowledge. The presence of emotion in the dataset caters the models with the ability to use additional information while reasoning about the dialogue act. The presence of emotion in the dataset caters the models with the ability to use additional information while reasoning about the dialogue act. There is another dataset, another example of why multimodality helps. Because we are having audio, video, and the text signal. So basically, these are videos and the audio signals help in understanding the proper dialogue acts. So only the text, if you only analyze the text, maybe there will be some ambiguity or the confusion. But if you can see the video or the audio signals, you'll be able to understand correctly what is the correct dialogue act. In both the examples, there exists inconsistency between modalities, which acts as a strong indicator that multimodal information is also important in providing additional cues for identifying DAs. The availability of complementary information across multiple modalities improves the model's ability to learn discriminatory patterns that are responsible for this complex process. So like, fine, then you tell Roger because he was really looking forward to this. So here the text is suggesting some agreement or the opinion. Audio is a commenting tone and video is basically furious. So you understand that sometimes if you see the audio and the video, you will be able to understand that text is not correct. So from the text, there is some other understanding. That is very amusing indeed. So here text implies agreement, but the audio implies sarcastic tone and video is basically slight anger. So again, you can understand there is a disagreement between the modalities. So we developed a methodology which is called the multimodal feature extraction. So basically, you know, for in any multimodal system, the first task is to extract the features. So features are basically of three types. First, we have to extract features from the text. Then we have to extract features from the audios. And finally, we have to extract some features from the videos. So the feature extraction module is basically of three types. So textual features, the transcriptions available for each video forms the source of the textual modality. So pre-trained globe embeddings of dimension 300 is used to obtain representation of words. Word embeddings of each word are concatenated to obtain a final utterance representation. So basically, globe embedding is used to represent the vector representations of the words, and then the word embeddings are concatenated to obtain a final utterance representation. Now the second modality is the audio modality. To get the audio features, to extract the audio features, to elicit features from the audio, Open Smile and open source software has been used. The features are concatenated together to form a 256 dimensional representation for each window. The final audio representation of each utterance is obtained by concatenating the feature vector for every window. So basically, audio features are basically extracted by the Open Smile and open source software. So basically, we get a representation of the audio signals. And for the video features, we have used the ImageNet, which is a kind of CNN architecture. So ImageNet, pretend ResNet image classification model has been used. The visual representation of each utterance is obtained by concatenating the 4096 dimensional vector for every frame. So basically, these are the three features which we have extracted. So the first is the textual feature, which is extracted by using the globe embedding. Open Smile software is used to extract the audio features, and the video features are extracted by the ResNet 152. So then, textual modality, three individual bi-LSTMs are used for learning different semantic dependency features. One bi-LSTM learns DAC features tuned in accordance with the emotion features. Then second learns features for the emotion recognition task regulated by the learning of the DA features. And the third bi-LSTM learns private features for the task of DAC not influenced by the emotions. So there are basically three, bi-LSTMs. One bi-LSTM is responsible for learning the textual features of the only DAC task. Second bi-LSTM is responsible for learning the textual features of the emotion recognition task. And the third bi-LSTM is learning for learning the features of the emotion recognition task regulated by the learning of the DA task. So basically, this way, there are three bi-LSTMs which are used. And audio and video modalities, audio and video features are passed through a fully connected layer to learn attention of different variants. So you can understand that for the text, there are three bi-LSTMs. And for the video, there are some multi-layer perceptrons. And for the audio, there are some connected layers, fully connected layers. Then we also apply the attention. Yes or no?
Ma'am, in the previous slide,
Yeah.
why do we need three LSTM, ma'am? I mean, the third one, what is the usage, ma'am? Because in your paper, you said you need multimodal classification. You wanted the emotions. So why are we having a LSTM that is not taking emotions into consideration?
Yeah, so see, there are three LSTMs. The first LSTM learns DSC features
Yes,
tuned in
ma'am.
accordance with the emotion feature. Okay.
Yes, ma'am.
The second LSTM learns features for the emotion recognition task regulated by the learning of the DA features. And
Yes, ma'am.
third is basically the private features for the DSC, because here our primary focus is on the DSC task. We are not aiming to solve the emotion recognition task. We aim to solve the dialogue and classification task. Emotion recognition is our auxiliary task. So we just want to show, because our primary task is a dialogue and classification. So we just want to show that incorporation of the emotion features help in improving the DSC task. Okay. So our
Okay,
focus
ma'am.
is not on emotion recognition, because emotion recognition, there are many existing approaches. And this is the first work on multimodal DSC. So our main focus is on multimodal DSC. We only want to show that emotion features help in identification of DSC.
Oh,
That's why we have used only three LSTM, not four LSTMs. We could have used another LSTM for extracting private features of emotion recognition, but as our main focus is not on emotion recognition, so we have not used any private features of the emotion recognition.
okay, ma'am. Okay, thank you.
So then, we have used three types of attention networks. So each of the concept similar to basically each of these representations from the modality encoders are passed through three fully connected layers, each termed as query, key, and value. So there is a self attention. Self-attention is computed, 5 triples of Q, K, V, 3 from textual modality encoder, 1 from the audio and the video encoder are obtained. Then we apply self-attention. Self-attention is computed for all these triples by computing the matrix multiplication of all its corresponding queries to its corresponding keys. Then intermodal attention is basically also used, and then inter-task attention. So we have 3 attentions: self-attention, intermodal attention, and the inter-task attention. So finally, we fuse all the attention vectors. 13 different attention outputs for different tasks and modalities are computed from its corresponding attention scores. Mean of different attention outputs in varying combinations are computed to obtain final representation for each of the modalities and tasks as this. So appropriate weight is given, and then we are getting the sentence representations for the dialogue act classification and sentence representation of the emotion. Okay, so these are the attention vectors, and we are putting some weightage on the attention vectors. And then we are getting the final sentence representations for the dialogue act, final sentence representation of the emotion. And finally, basically the sentence representation for each of the tasks from the TAs are connected to a fully connected layer, which in turn consists of output neurons for both the tasks. Okay, so finally this is the sentence representation of the dialogue act classification. This is a sentence representation of the emotion. Both are passed through some connected layers, and then we are predicting the dialogue acts and the emotions. The errors computed from each of these channels are backpropagated jointly to successive prior layers of the model to learn joint features of both the tasks. So the errors computed from each of these channels are backpropagated jointly to the successive prior layers of the model to learn joint features of both the tasks. So basically, these are the results on the analysis. So we have, as I mentioned, we have there are 2 tasks: emotion recognition and the dialogue act classification. The primary task is basically the dialogue act classification. Emotion recognition is basically the auxiliary task. So we have performed experiments on the emotive data set. Experiments were conducted by segregating dyadic and multi-party conversations, as well as in addition to the whole data set for the multitask framework, along with different modalities. Multitasking framework performs consistently well compared to the single task DSC variant. So here you can see the results. So this is the only single task. So when we are only solving the dialogue act, and when we are solving the dialogue act with the emotion recognition, okay. And this is the dyadic data set, and this is the multi-party data set, and this is the whole data set. And we have done a ablation study, like we first perform experiments with only text, then only with audio, then only with video, then text plus audio both, audio plus video, text plus video, and then 3 together. And also we have added with the video, we have added the emotion feature separately, and then we have shown that our results, like these 3 modalities perform the best. And also the multitasking is basically better. Multitasking is better than the, we can see that T plus V provides the better result, and T plus V is basically T plus V is better for the multitasking also. So these results prove that multitasking helps. Also the multimodality helps. So these are some utterances, like, she is not Larry's girl. So it is the true level is disagreement. Our multitask model is giving disagreement, but the single task is giving statement. I know it was amazing. I mean, we totally nailed it. It was beautiful. So the true level is agreement. Multitasking is given as the agreement, but the single task is given as the others. So this way you can see the single task is making more mistakes than the multitask. Multitask is somehow similar to the true level, but single task is making many mistakes. And these are the different types of attentions. So we have done early fusion, late fusion, hypothesis level, different types of attentions. So we have did a ablation study of the attentions. And then our proposed approach where all the attentions are used, so that performs the best in terms of the F score and the accuracy. And these are the results that when we are doing multitasking, like when we are solving DSC plus ER together, focus is given on the right word. Like, oh yes, yes, I am. You can't stop me. Here, this can't word is very much important, and me is also very much important. So yes, you can see that the focus is given on these words. So this is all about dialogue classification. So I have shown how dialogue classification can be solved in single task framework as well as in some multitask framework, and how the dialogue classification can be done only from the text. Like initially, I have shown you some machine learning, deep learning based classifiers for solving the dialogue classification. And then I have shown you how some multimodal approaches where we have audios, videos, and the text. So how multiple modalities can be useful for solving the dialogue classification. And there in that framework, we have solved two tasks together, the dialogue classification and the emotion recognition. So now there are two tasks, intent detection and the slot filling. So you would like to discuss about these two tasks together. So intent detection and slot filling is the task of interpreting user comments or queries by extracting the intent and the relevant slots. So intent detection is framed as a classification task which maps an observation sequence to a particular label to acquire the most probable intent label given some word sequence. So intent detection is framed as a classification task which maps an observation sequence to a particular label to acquire the most probable intent label given some word sequence. And slot filling is also a classification task. It is a sequence labeling task. Like here you can see that first class fares from Boston to Denver. So here the intent is airfare because the customer wants to know about the airfare. And what are the slots? So the first is the beginning of the class type. Class is the intermediate of the class type. Fares is others. From is others. Boston is the B of from location. To is the others. And Denver is the B of to location. So slot putting is often framed as a sequence labeling task, which maps an observation sequence to a sequence of labels, that is to acquire the most probable slot sequence given some word sequences. So in the here there are many available datasets like ATs, which contains user utterances related to the air travel information system. Then there is this NIS, SNIPS contains several day-to-day user comment categories like play, song, book, a restaurant, etc. MIT restaurant movie corpus contains user utterances related to movie and restaurant domain. So there are several datasets available. And we have basically proposed some deep learning based architectures for solving this, for solving the problem of intent and the slot filling. So basically, our proposed architecture is using the LSTM or GRU plus CRF. So this particular approach combines a LSTM GRU network with the CRF network. So CRF is used for slot filling. So as I mentioned, that slot is a sequence labeling task. So you have to predict the sequence of labels like B class type, I class type, others, then B from location, B to location. So all these are basically sequences of labels. So basically, this is called the slot filling. So the idea behind such an approach is that this network can then efficiently utilize the past input features because of the presence of the LSTM layer, followed by a CRF layer, which can then add sentence level tag information. So we are using the LSTM layer, followed by the CRF layer, which can add sentence level tag information. So LSTM is used so that the context can be preserved. CRF layer predicts the current tag with the help of past and future tags, which is quite similar to a bidirectional LSTM or GRU network that makes use of past and the future input features. And the model 2 is basically using the by LSTM or by GRU with a CRF. The model combines a bidirectional LSTM or GRU network and a CRF model to obtain a bi-LSTM GRU CRF model, along with the past input features and sentence level tag information. The model utilizes the future features as well. So basically, bi-LSTM is capable of checking both past and the future. So that way, basically, it can understand the context present in the past and the future. That's why the BioLSTM is very much useful. So we basically developed two models. In the first model, LSTM is basically used for extracting features, and CRF is basically used for the classification. And the second model, BioLSTM or BiGRE is used for the feature extraction, and the CRF is basically used for the classification. So this is the thing that bi-LSTM GRU CRF network. So we are giving the input show flights from Tacoma to Nass Valley. So then we are passing through GRU or bi-LSTM, and then we are predicting the levels like others, brief from location, city name, others, B2 location, city name. So this way we are basically predicting the class levels. Then here, this is a bi-LSTM GRU CRF network. So bi-LSTM GRU CRF network, again, there will be, that we are taking the context from the past and the future, and then we are basically predicting the class levels, which are the slot levels. These are the results. So we have compared like simple LSTM, simple GRU, bi-LSTM, bi-GRU, only CRF, then LSTM plus CRF, GRU plus CRF, bi-LSTM plus CRF, bi-GRU plus CRF. So bi-LSTM plus CRF is giving us the best result. So bi-LSTM plus CRF is giving us the 98% accuracy and 97% F1 score. So basically, these are the results of basically this is the work on intent and the slot identification. And now I will basically you understand that dialogue systems is having many components. So one such component is basically dialogue classification. Then the second is intent classification. Third is slot filling, and then comes the dialogue manager. So dialogue manager is a reinforcement learning based. So the task of the dialogue manager is to map the state into action. So state is comprising of multiple variables. Mostly state is comprising of all the slots. And slots are basically extracted by the slot filling module. So the slot filling module used to extract the slot values, and those are given as a state. And then the dialogue manager maps the state into an action. So now we were going to discuss the dialogue management component. So till now, do you have any question? Like you can please ask because already 1 hour is complete. So now we are going to the next portion. So if you have any question, you can ask me. Anybody having any question?
Ma'am.
Yes.
So in these papers you spoke about data sets, no ma'am?
Yeah.
Data sets were specific for a particular situation. So how would you come up with a general conversational agent, ma'am?
No, so if you want to develop a general conversation agent, you have to first fix a domain. Okay, like suppose you want to develop an agent, you it can't be a very much general. You have to first
Okay.
fix a domain that you want to generate a chatbot for a restaurant domain, or for a movie booking domain, or a flight booking domain. So you have to fix a particular domain, and then you have to generate the conversations of the particular domain. So it is not possible like a single agent. Yes. So if you have multiple domains and if you have data from the multiple domains, then your system can be able to understand the different domains. But otherwise, in general, we used to fix the domain and accordingly we gather data. Yeah, but data collection is very much important in dialogue systems because you understand that nowadays the focus is on deep learning based techniques. So all are mostly for almost all the components that dialogue acts, intent classification, intent detection, and then dialogue managers we will see. So for almost all the components, deep learning based models are most popular. So, and deep learning based models are very much resource hungry. So
Yes,
they
ma'am.
require huge amount of data. So generation of data is very much important. So you can check my papers, like I have mentioned that all these works are basically published in reputed journals. So you can check our papers to know more about the data sets.
Okay. Thank you.
Yeah. Okay, so then let me go discuss the dialogue manager part. Dialogue management, I hope my slides are visible. Could you please confirm?
Yes, ma'am.
Yes.
Yeah. So dialogue manager is basically here a special kind of machine learning approach, which is called the reinforcement learning. So this reinforcement learning are basically popularly used for dialogue management strategy. So basically we will see what we mean by reinforcement learning. So dialogue management strategy is the most, basic key part of a dialogue system, because you extract information from the user utterance. So that is called the natural language understanding. So I have already mentioned that natural language understanding is having three components: dialogue act classification, intent detection, and slot filling. So by using these natural language understanding modules, you can extract useful information from the user utterance, and this information can be used as a state information, and this state can be mapped to mapped to a action. Okay, this state can be mapped to a action by using the dialogue manager. So what would be the next action of an agent? So that is decided by the dialogue manager. So given a user utterance, what would be the next action of an agent, that will be decided by the dialogue manager. So basically, the main function of the dialogue management component is to control the flow of the dialogue. It involves the following task: determining whether sufficient information has been elicited from the user in order to take a suitable action, and then execute an action. So either you have to communicate with an application, or you have to communicate with the user. Okay. So basically, you know that whenever there is a user utterance, after analyzing the user utterance, the agent has to take an action. So this action could be like you have to search in a database and you have to retrieve some answer, or maybe you have to re-ask some questions. So there could be many such actions. So basically, we execute an action means you have to communicate with an application and you have to communicate with the user. So this is the situation. So reinforcement learning allows the machine or the software agent to learn its ideal behavior based on feedback from the environment. So there is the agent, which is the dialogue agent, and there is the environment. So agent is picking an action. This action is given to the environment, and then there is a state information. So this state is basically, is the collection of slot values. Mostly the state is basically the collection of slot values. So that depending on the state information, the agent picks up an action. And then this action is given to the environment. And whether the action is good or bad, so depending on the quality of the action, some reward or some penalty function can be introduced. So if the action is very good, like the action picked by the agent is really good, then there will be some reward function. And if the action is not good, then some penalty will be imposed. So RL allows the machine or software agent to learn its ideal behavior based on feedback from the environment. It is the rewards. So below is a block diagram of a typical RL setup. The underlying principle behind RL is law of effect. You do something, something good will happen. So you try to do it more often if a similar situation arises. You do something bad happens. So you try to do it less often if a similar situation arises. So this is the idea of the RL. So you don't really know the actual output, like actually given a state, what will be the exact action, that is not known, but we can only judge the quality of the action. So given a state, some action is picked up. Whether that action is appropriate or not, So that can be judged by a reward or a penalty function. So reward means the action is very good, and the penalty means the action is not good. So while RL, carefully the dialogue management strategy employed is completely rule-based. Okay, so mostly it was a rule-based that if you see this state, take this action. If you see the other state, take the other action. This way, a rule-based system can be used. And then, but rule-based system is, it is a handcrafting rules. So the reinforcement learning can help in minimizing the use of the handcrafting rules. And reinforcement learning is data-driven. So based on the data, we can analyze the reward functions. So the reward functions can be easily calculated based on the data. To exploit the recent advances in reinforcement learning and the deep learning, and it helps in end-to-end synthesis. Now there is no rule-based system because I have already mentioned that dialogue act classification intent and the slot can be developed by using deep learning-based frameworks. And now dialogue manager can also be used, can also be developed by deep reinforcement learning-based frameworks. And that way it will be an end-to-end system, dialogue system. Create an infrastructure that will be used across different domains. So a RL chatbot takes an action at time t, which is converted into speech by text-to-speech unit. So the reinforcement learning chatbot takes an action at time t, which is converted into speech-to-text, speech by text-to-speech unit. Okay. So basically, RL chatbot is taking an action, and that has to be translated into speech by text-to-speech unit. The user's response in the form of speech is converted to text by speech-to-text unit. The output of the STT unit, that is the observation, is received by the chatbot. The user may either generate a reward signal explicitly or it is derived from the user's response. Okay. So given an action, the reward signal could be generated explicitly or it is derived from the user's response. The task of the RL chatbot is to respond in a way so as to maximize the reward. So basically, it is an optimization problem. The task is to pick that particular action or to pick that sequence of actions which can maximize the reward. So this is our RL chatbot. So basically, there is a chatbot. Chatbot is picking up an action. Action is translated into speech to text. Text to speech by a text to speech unit. Then this speech is given to the user. Now the user is based on the environment, some reward is given to the chatbot, and user is uttering utterance that is translated by speech to text into an observation which is given to the chatbot. So this way, a RL chatbot is basically generated. So reinforcement learning, thus any RL setup is mathematically described in terms of an abstraction called the Markov decision process. So the Markov decision process is basically described as finite state space. S is the finite state space. A is the finite action space. R is the reward model. T is the transition model. And ROH is the initial state distribution. So a Markov decision process is described by a tuple. So in the tuple, there are many components. S is the finite state space. A is the finite state of actions. R is the reward model. P is the transition model, like transition model which from a particular state it will jump to some other state. So this transition model is basically modeled as P, and RHO is the initial state distribution. The idea is to implement RL for learning dialogue strategies using the Q learning algorithm. So basically, in Q learning is a particular RL learning algorithm. So there is a Q function which is a quality function. So Q stands for the quality. So this quality function helps in predicting, helps in understanding the quality of a particular action. The main idea in Q learning is that we can iteratively approximate the Q function using the Bellman equation. So there is a dynamic programming concept. By using the Bellman equation, we can approximate the Q function. And Q function is the quality function. Hence, the Q function will be approximated using a neural network. Incorporation of deep RL. So the Q learning defines a function QSA, which represents the discounted future reward when we perform action A in state S and continue optimally from that point. So the Q learning defines a function QSA, which represents the discounted future reward when we perform action A in state S and continue optimally from that point on. The way to think about QSA is that the best possible score at the end of an episode after performing action A in status. Okay, so QSA is the quality function. So it is basically a kind of reward function. It is the best possible score at the end of an episode after performing action A in status. It is called Q function because it represents the quality of certain action in given state. So it is called Q function because it represents the quality of certain action in given state. If you want to select the action that results in the highest score at the end of an episode, so pick the action with the highest Q value. So the main idea in Q learning is that we can iteratively approximate the Q function using the Bellman equation. Here gamma is the discount factor between 0 to 1. The more into the future the reward is, the less we take it into consideration. So this is the basically Bellman equation. So by this Bellman equation, we are optimizing basically approximating the Q function. We basically approximate the Q function. So deep Q network is basically a deep learning based network which approximates the Q function. So in deep learning based neural network, reinforcement learning, in DRL, deep learning based reinforcement learning, the Q function is implemented and approximated using a neural network. So the neural network basically tries to approximate the Q function. So it acts as a function approximator. We can take any number of possible states that can be represented as a vector and learn to map them to Q values. The Q function of a DQN agent is parameterized as DQSA theta I, where theta i's are the parameters or the weights of the neural network at iteration I. So theta i's are the parameters or the weights of the neural network at iteration I. A Q network can be trained by minimizing a sequence of loss functions that get updated at each iteration I as follows. So a Q network can be trained by minimizing a sequence of loss functions that get updated at iteration I as follows. Where theta i's are the parameters of the neural network at iteration I, and theta i's dash are the target parameters of the neural network. So this is the error function, and this error function is basically this error is minimized in the neural network. So this way, deep learning can be used for reinforcement learning. So there is another concept which is called the double Q deep Q network. So the one issue with the deep Q network is that it is more likely to overestimate the Q function values due to the Maxine equation, which is used to set targets. So rather than doing that, now there could be two separate DQN deep Q networks. It is called a double deep Q networks, Q1 and Q2. So DDQN algorithm is set to overcome this particular problem. In this algorithm, two Q functions Q1 and Q2 are independently learned. One function is then used to determine the maximizing action, and second to estimate its value. So basically, one is used to approximate the action, determine the maximizing action, second to estimate the value. So this way, double deep Q network is basically used. And then third is the priority experience replay. Another concept that is acknowledged in the literature is how the experiences are used for training. To know that some samples are more important and you can put emphasis on those samples. So that is called the priority experience replay or the PAR. When all the samples are treated alike, one of the aspects which gets ignored is that learning happens more from some conditions than from others. Some instances are more important for learning that Q network, and some are less important. The PAR is one such strategy that tries to leverage this fact by changing the sampling distribution. The main idea is that those transitions are preferred that do not fit well to the current estimate of the Q function. So now we will show you how reinforcement learning can be used to solve the dialogue management problem. So this, in this particular work, so we have developed a hierarchical deep dialogue manager. So already somebody has asked me that if there will be multiple domains and there will be multiple intents. Sometimes, when user is asking about the student, maybe initially he was interested to book a flight, but after that he can immediately jump to book a hotel. Initially, he was asking to book a flight, and then he asked to book a hotel. So there is a transition in the domain. Similarly, some utterances can have multiple intents. So we have to develop a hierarchical dialogue management strategy for task-oriented virtual agent for managing multi-intent conversations using reinforcement learning. So basically, here the task is to manage multi-intent conversations, develop a hierarchical dialogue manager strategy for task-oriented virtual agent for managing multi-intent conversations using reinforcement learning. So intent captures the main communicative intention of the user utterances. Multi-intent captures more than one intention present in an utterance. So you know that intent, we already know that intent captures communicative intention present in a user utterance. There are many examples where there are multiple intentions, like only flights and cheapest fare from Pittsburgh to Delaware. So there are multiple intents like flight and the airfare. So how to handle this kind of utterances where there are multiple intents? So for that, we have developed a basically hierarchical framework. In the first hierarchy, we have to deal with the intents. So you have to recognize what is the current intent. See, if there are multiple intents, so then multiple intents will be detected. And for each intent, there will be a neural network. So there will be a DRL. So each intent will have its own network, and that will be responsible for fetching information from the user. So basically, in order to solve the intent, you need to extract some information in the form of slots from the user. So basically, this there is a global slot tracker. Global slot tracker is having many slots, and we have to extract the slot information from this global slot tracker. And depending on the intent, we have to switch amongst the intents of the DRL model. So they suppose multi-hot encoded intent state space. So you have to switch between one intent to the other intent. So end of intent moving to next intent, and to and from conversation of the VA and the user. So basically, this is the whole hierarchy. There are two hierarchies. In the first level, we have to predict the intent. So for a particular intent, there is a particular network. So we have to invoke that network to fill up the slots. So this is the thing, user utterance is given. Then there is an intent module. Intent are identified from the user utterance. Then a particular network is invoked, and this network is responsible for filling up the slots. And then finally, basically, end to end of intent moving to next intent, and to and from conversation of the VA and the user. So network of reinforcement agents. So train a set of networks where each network represents servicing a particular intent to complete a particular sub-dialogue. Each DRL network exhibits unique behavior while interacting with the user to complete its task optimally. So basically, there are two layers. The lower level layer is responsible for picking up that action which maximizes the Q function. Each DRL network exhibits unique behavior while interacting with the user to complete its task optimally. Therefore, in a network of deep reinforcement agents, an action selection is performed based on an optimal policy. Okay, in the lower level, there is an optimal DQN network. So DQN network is responsible for selecting the appropriate action. So DQN network is used for lower level hierarchy. It is within a DRL model transition where intent is determined based on the higher level network. So the higher level hierarchy is used to select the intent, where feature F comprises of all the features, specifically the word vectors that are used to represent the user utterance. G is prerequisite for network of deep reinforcement learners, where G represents the IC. So basically, there are the state space is having now basically in the state space there are two components. One is the intent, and other is the slot. So the S1 is basically it is a state which is a tuple of n variables corresponding to the number of intents in the particular domain. So suppose a particular domain is having 10 intents. So this is a binary vector of having 10. So the individual values represent whether that intent is present or not. So it keeps track of the current intent output from the IC module or the intent intent detection module being served by the VA in the form of one hot encoded vector. This in turn invokes the appropriate RL model corresponding to the intent being served. So basically, as this is a hierarchical model, so there are two components in the state vector. One is the S1, another is the S2. So S1 is basically for the intent. So the binary vector is basically kept. So size of the binary vector equal to number of intents. So if a particular intent is present, then that value would be 1, other value would be 0. And S2 is basically the slots. So suppose S1 is basically this in a particular intent is present, and the corresponding slots would be present in the S2. So S2 is the global state tracker. All the slots which are responsible for a particular intent would be present in S2. The generic architecture of MDP is used. It finds its applicability in any domain having n number of intents, m number of slots. S2 for each of the intents, S2 is a tuple of variables of the length equal to the number of slots required to fill up the particular intent. So a particular intent may have multiple slots. So all the slot values are present in S2. This state represents the bottom level hierarchy because S1 is the intent, which is the top level hierarchy, and S2 is the slot, which is the bottom level hierarchy. These slot variables in turn correspond to confidence scores of different slots, which are the probability values outputted from the SF module, representing the confidence of the module in predicting different slot levels. So these slot variables in turn correspond to confidence scores of different slots, which are the probability values outputted from the SF module, representing the confidence of the module in predicting different slot levels. And in this case, there are many actions. So basically, there are 21 unique actions categorized in 3 different classes: ask, re-ask, and salutation. So basically, such as ask class, re-ask, GCT, etc. So basically, there are 21 unique actions. Now, what about the reward model? So it is a reinforcement learning, and I mentioned that in reinforcement learning, reward plays a very important role because reward only helps to identify the correct mapping between the state and the action space. So here the different reward function at different time steps for different actions in conversation. For any action except terminating action, so this is the reward W1 into NS minus CS. NS is the next state and CS is the current state. So what do you mean by state? The state is the collection of, basically it is the lower level state representation. So the lower level state representation, state is nothing but the collection of slot values. The probability values of different slots are basically the state representation. So the NS is the next state. So here we have the slot values. So all the probability values of all the slots, and then the CS is the current state. So after taking a particular action, will there be any improvement in the current state? So any slot value will improve or not. So that is basically checked by this reward function. So after picking a particular action, if some slot value gets some improved value, so there is an increment in the in the slot value, then that is basically, then this difference will be positive. And we multiply with W1. So W1 is used to encourage the agent to act in a way so as to increase confidence on the acquired slots. And W2 is used to discourage unnecessary questions in relation to the user. So basically, this is our reward, W1 into NS minus CS minus W2. So now there are some terminating reward action. For terminating action, the condition is that how many slots has a confidence score above a threshold say 0.7. The condition is satisfied when all slots match the criteria. If the condition is not satisfied, the reward function is minus W1 into EV minus CS. EV is the summation of maximum expected confidence scores of different slots. So basically, this is the condition. The terminating condition is that all the slots should have value greater than 0.7. And if all the slots do not have the values greater than 0.7, then the condition is not, terminating condition is not satisfied. In that case, EV is basically, we expect that all the slots should have the value 0.7. So that is the expected expected state minus the current state. And this is a penalty, though we have not reached the terminating state, but we have somehow selected the terminating action. So there is a penalty for the same. Otherwise, if the terminating condition is satisfied, that means all the slots are having probability value 0. More than 0.7. Then basically reward is W1 into CS. CS is the current state. So these are the learning curves, the different learning curves. So you can see that over the iterations, how the learning curves vary. So you can see that for different maximum this markup decision processes, these are the curves. And verbalization of the system, like agent is asking, "Hello, how can I help you?" User is saying, "I would like to travel from Pittsburgh to Denver." I would like to travel from Pittsburgh to Denver. So basically, you have to find out the intent. So only one intent is present, and these are the S2 is the corresponding slots. Then agent is picking up the action ask class. So there is a translation. Please specify the class of flight. User is saying, "I want to travel in economy class." So here again one intent is present, and these are the corresponding slot values. Then the agent is picking up the action ask date time. So specify the time and date. So user is saying, "Oh, on 4th January at morning." So these are the NLU outputs. Then agent is asking closing the flights from Pittsburgh to Denver on 4th January at morning by economy class are this. So this conversation continues. So now how to develop a virtual agent in Hindi? We intend to exploit the fact that even though there is a language difference, but the semantic relation of a specific task coexist irrespective of any language barriers. So dialogue management component is basically same for all the languages, because dialogue management component, the task of the dialogue management component is to map state into action. So it was in different languages. So NLU module will vary because NLU module has to understand the language, but the same DM component which is used for the English can be used for the Hindi as well. Because DM component takes input as slot, which is the probability values of different slots, and the outputs a particular action. So for English and for Hindi, there is no difference in the input-output scenario. So thus we have reused the same DM module which is trained on the English for developing the VA in Hindi. Only there is a change in the NLU module, because now the NLU module, that is the inter-interaction, slot filling, or the dialogue classification module, they have to somehow understand the Hindi dataset. The IC and SF module have been trained on the semantic tagging purpose developed in Hindi for the 80s dataset. Following this similar approach, the DM module can be reused for any other language for the related task, given that there is an availability of the semantic tagging corpus for the task in that given language. So this is the results of the, so you can see the same DM component can be reused for developing the VA in Hindi. Now we have also developed some sentiment-aware dialogue management policy, because till now our reward functions are task-based reward. So whether a particular task is completed or not, that was our main concern. But we have not focused on basically making the user happy. So in a dialogue, in a chatbot environment, one important aspect is we need to develop such a chatbot which is making the user happy. So user sentiment should not become negative in at any point of time. So that is basically another task that we want to develop some reward functions which are also based on the sentiments of the user. So if suppose after taking a particular action, we are making the user unhappy, then there will be a penalty. But after taking an action, if there is a if you are making the user happy, then there is a reward. So learn a dialogue policy for multi-intent conversations using hierarchical reinforcement learning. Here, there is another advantage that now our system will be able to understand. So that when the user is chatting with the chatbot, it can not only show some text but can also show some images. So it can display some text as well as it can display some images. So our chatbot will be able to extract information of the slot values not only from the text but also from the images. So our natural language understanding module is now multimodal. So it can capture information not only from text but also from the images. So the VA should be capable of handling multimodal information from the user in terms of text and the images. User behavior, apart from semantics, such as sentiment, provides complementary information to better understand users. VA should learn sentiment-aware dialogue policy. So basically, in this particular task, there are two contributions. One is that now user can also chat using images and text both. So suppose user is not able to describe something by using text. So in that case, the user can simply post a picture to make the agent understood that what it is what the user wants to say. So the images can also be a medium of input. And the second is that there is not only task specific reward function, but also the agent's main focus is to make the customer happy. So if at any point of time, if the agent is becoming unhappy, then there will be a penalty. But if the agent is happy with the situation, then there will be a reward. So basically, this is the motivation. The needs and queries of the user are complex and composite. Eventual evaluators and consumers of any dialogue system are users. The extra feedback from the user in terms of sentiment will steer the VA to be user adaptive to learn an efficient dialogue policy. So in real life conversations, users communicate their choices or queries both using text, images, and verbal communications. So basically, our task is to use this multimodal information in the natural language understanding module. So our NLU module is not only able to extract lot information from the text, but also from the images. And the second thing is that this sentiment-based reward functions. So I proposed a novel dialogue policy learning framework to curate a VA that integrates hierarchical value function with deep reinforcement learning to learn strategies for managing multi-intent task-oriented conversations. So the VA is curated in a manner such that it is capable of handling multimodal information in the form of text and images communicated by the user in its learning framework. Along with it, sentiment of the user is incorporated to this hierarchical value functions to make the VA adaptive to the sentiment of the user. Large-scale dataset named vSentiVA for multi-intent conversations annotated with its corresponding intent slot and sentiment labels, along with the related images for communicating different entities for the restaurant domain is made available. So this is the data. This is the dataset vSentiVA. So dialogue, there is a dataset Barbie. So this Barbie dataset is basically used to curate conversations in the of his CENTIV dataset. So this dataset contains conversations concerning several intents such as restaurant information, restaurant booking, restaurant phone, restaurant address, involving slots or entities such as location, cuisine, number of people, restaurant name, and spice. His CENTIV dataset contains a lot of total of 1,286 dialogues modified for the presence of multi-intents in a particular dialogue, annotated for its corresponding intent, slot, and sentiment levels, along with visual communication of user's choice of a specific entity through images. The dataset contains a total of 1,460 images of various slots and its type. So this is the data set. You can see that user is saying good morning. Agent is saying hello. What can I help you with today? User is saying I would like a table for 2 in London in a moderate price range. Agent is saying I am on it. User is silent. Agent is saying any preference on a type of cuisine. User is not saying anything, but user is showing a picture. Agent is saying, did you say Chinese cuisine? User is saying, obviously. Agent is saying, what category restaurant are you looking for? User is giving this 5-star. Agent is saying, okay, let me look into some options for you. User is silent. Agent is AP call Spanish London to moderate. User is silent. Agent, what do you think of this option? It is giving some option to the customer. Then, so this way basically conversation is going on. And finally, user is saying, you rock. Agent, is there anything I can help you with? User is saying, no, thank you. Agent is saying, you are welcome. So this is our proposed module. So now you can see that this is the NLU module. So the NLU module, we also have an image identification module because users are sometimes posting the images. So from the images, we have to extract the useful information. So like from this image, the agent has to understand that the user is referring to a Chinese restaurant. Here it is a 5-star. So that way there is an image identification module. So user input is given, then extraction of semantic state space. So we have to extract information from the images as well as from the text. That is the state information. So date, today, number of people, 2, sentiment equal to neutral. Then there is this top level intent meta policy and the lower level intent meta policy. So there are 2 meta policies, top level and the low level. And then basically it is a hierarchical DM module. So the low level meta policy is taking an action, and that action is translated into system response by the natural language generation module. So this is the overall architecture of our proposed method. Now this is our multimodal state space extraction. So from the utterance, we are getting the embeddings. So embeddings are passing through the CNN followed by the multi-layer perceptron for the intent classification. Then there is this BiLSTM. So BiLSTM, we are passing through the BiLSTMs, then the multi-layer perceptron for the slot filling. Then embeddings are passing through the BiLSTMs followed by the multi-layer perceptron for the sentiment classification. And then there is this ResNet, which is the image-based extra image. So which is extracting the images from the images. So we are concatenating them together, and that is giving us the multimodal artificial semantic state space representation. So this is our multimodal space extraction. And we have also incorporated some sentiment-based reward. So as I mentioned, the sentiment-based reward means we want to make the user happy always. So if the sentiment is positive, then this is the corresponding probability is basically used as the reward. If the sentiment is negative, then 1 minus PS, the probability value is, if the sentiment is negative and the user is very much and the probability is high, then SZ will be a very small value. And if the sentiment is negative, and the probability is very low, then SZ would be a high value. And this is the sentiment-based reward. If there is the sentiment is positive, then we are giving a reward. If the sentiment is negative, we are giving a penalty. Otherwise, for the neutral, we are fixing a value of 0.5. So PS is the probability value outputted from the P10 sentiment classifier. So our sentiment classifier is a bi-LSTM based classifier. So from the sentiment classifier, we are getting this probability value. So probability value outputted from the P10 sentiment classification module for a given user utterance. Thus, the proposed reward at every time step of the conversation is basically we have the task-based reward plus the sentiment-based reward. The results show that these are the learning curves. So you can see our average reward increases rapidly with the incorporation of the sentiment-based reward and the task-based reward. So there is a rapid increase in the reward, average reward, with the incorporation of task-based reward plus the sentiment-based reward. So these are the basically performance of the PS during testing. So during testing, you can see the user, we have performed the user satisfaction. So user TR plus SR plus multimodal. So that is giving us the more satisfaction. So we like amongst the 100. So if you are using only task plus reward, then 72 for the 72 cases user is satisfied. For the sentiment case, only 69 cases user is satisfied. But for the task based reward plus sentiment based reward plus multimodal architecture, for the 87 cases the user is satisfied. Similarly, for the average number of turns, so TR plus AR plus multimodal is taking only 14 number of turns, which is the minimum amongst all. So these are the results. Like one example, like how sentiment based reward helps us to understand to basically pick the correct action. Like, what do you think of this option? Agent is asking. No. Do you have something else? Then the user can easily understand that from this thing it is a negative sentiment. So from this negative sentiment, the agent can understand that the user is not happy with the option. So the agent can show the next option. Sure, let me find an other option for you. What do you think of this option? Let's do this. So agent, this option is available. No, do you have something else? Is there anything I can help? So here, see, if the sentiment-based reward is not available, the agent is not able to understand that the user is not happy. The agent is not able to understand the user is not happy with the option. It has to show the next option. That is, that information is not conveyed to the agent. But if you are using the sentiment-based reward, then that information is conveyed to the agent. So image identification error. So like there are some errors as well. Like if the upper image gets misclassified as the lower. So basically, you know that in some cases there is an ambiguity. It's very difficult to determine whether this food belongs to is a Chinese food or a seafood. So basically, you know, it's very difficult to understand whether this is a Chinese food or a seafood. But the upper image gets misclassified as the lower. So next, basically, we have worked on the transfer learning based approach. So we developed some, as somebody has asked me that if suppose you have to develop a chatbot for multiple domains. So maybe initially you developed a chatbot for the restaurant domain. Now can we use the same chatbot for the hotel domain? So basically, transfer learning can help us in reducing the training time. So basically, transfer learning we have used the transfer learning based system, transfer learning based task oriented dialogue policy for multiple domains using hierarchical reinforcement learning. So to develop a multi-domain, multi-intent based task oriented dialogue system by successfully combining hierarchical deep reinforcement learning and transfer learning paradigms. So basically, we have developed a multi-domain, multi-intent based task-oriented dialogue system by successfully combining hierarchical deep reinforcement learning and the transfer learning paradigms. So to develop a multi-domain, multi-intent based task-oriented dialogue system by successfully combining hierarchical deep reinforcement learning and the transfer learning paradigms. So why hierarchical reinforcement learning? Because you know now there are multiple domains, there are multiple intents. So basically there is a hierarchy. In the previous case, we have seen there are two hierarchies, one for the intent, another for the slots. And now there are three hierarchies, one for the domain, second one is for the intent, and third one is for the slots. It gives VA the capability to handle complex and composite tasks of the user pertaining to multiple domains. By transfer learning, the notion is to exploit or take advantage of the resemblance between the source and target domain. So suppose source and the target domain are very much similar, like restaurant reservation and the hotel reservation. They share they share considerable amount of overlapping data or attributes in terms of slots. So restaurant and hotel reservation share considerable amount of overlapping data or attributes in terms of slots. Previous works were focused on creating end-to-end VAs independently with domains in isolation, such as one for restaurant, air travel, movie, etc. So these domains have common or overlapping attributes such as location, time, number of people, and so on. Intuitively, this information need not be learned multiple times pertaining to individual domain, and that a transfer is indeed desirable and feasible. So basically, this is our contribution, successfully combining transfer learning with hierarchical reinforcement learning, specifically options framework, to build multi-domain, multi-intent based dialogue system. So now this is the thing that we have multiple domains, and we do not want to develop the chatbot from the very beginning. But the source domain, there are two domains, source domain and the target domain. So suppose we have already built a chatbot for the source domain. So we want to transfer the same chatbot for the target domain. So we don't want to start from the scratch, but we want to use the pre-trained models of the source domain to develop the chatbot in the target domain. That is the utility of transfer learning helps faster and better convergence of the dialogue policy for the target domain compared to the ones trained independently. The proposed approach aims to reduce the data requirement to train multi-domain VAs significantly while averaging from the transfer learning based approach. So this is the thing that at the very beginning we have the domain policy. So domain policy will determine which domain. So it will basically determine the domain, and then accordingly it will basically decide about a particular intent policy. So each domain is having multiple intents, and for each intent there will be individual networks. So each intent will have individual network. So first at the top level we have to identify the domain. Then the domain will identify the intents, and for each intent there will be one individual module. So this way basically this will be a hierarchical architecture. So first we have to invoke a domain policy. Domain policy will invoke a intent policy. Intent policy will invoke a controller policy. So this way basically now what will happen if there are multiple domains. So in that case, this domain is having multiple intents. This domain is having this set of intents. Can we somehow map like this intent one based on the similarity? Can we map this intent one to intent two of the domain two? So depending on the semantic similarity, can we make a mapping between the intents of the first domain to the intents of the second domain? Then the corresponding network weights could be copied. Like there is a network for the intent of the domain one. So the same network can be used for training the intent of the domain two. So that is basically our proposed approach. So without transfer learning, the two domains are trained independently, where the weights of the network of each domain are initialized randomly, which produces dialog states from unique to distinct distributions. Also, the output space of the set of actions are as well independent of the other domains. We apply transfer learning from the source to the target domain only for the low-level controller policies, because VA interacts or elicits information from the user with the help of only the low-level controller policies. Rest of the higher-level meta policies help decompose the composite task into multiple subtasks in different granularities not known to the user. In order to leverage from transfer learning, it is essential to model the dialog state for both the source and the target domain such that it came from the same ordered identical distribution. While training the controller policy for the source side, the state of the dialog depends or must also incorporate not just the slots explicit to the source domain, but also those that are present in the target domain and vice versa. So basically, we have to, this is the thing that there has to be some mapping. Like this intent must map to this intent semantically. this intent 2 can map to some other intent of the domain 2. So there are two domains, source domain and the target domain. So each intent is having, and each domain is having multiple intents. Okay, and each intent is having a controller policy, which will decide the state to action mapping. So now we have to do a matching, like this intent 1 can be mapped to this intent 1 based on the slots, and the actions have to be same, have to keep the same. So similarly, the set of primitive actions need to be shared as well. The controller policy specific to the source domain must now also be aware of the primitive actions of the controller policies of the target domain, even if most or none of these slots or actions are ever used in a particular domain and vice versa. This imposition is mandatory, arising from the fact that it is impossible to reduce the neural network weights if the input and output space differ from domain to domain. For transferring the knowledge, two criteria is followed. Firstly, we choose subnetworks or controller policies which are semantically similar or have significant overlapping slots with each other in between the source and the target domains. And secondly, even if the intents do not semantically represent a similar thing, we can still exploit the existence of similar slots in unrelated intents. So that way we have to do some mapping between the intents, and then the inputs and the outputs have to be remain similar. So that's all the slot values of this intent and this intent should be present in the input, and all the actions of this intent plus this intent should be present in the output. So all the networks, so intent one's network and here the intent one network, as they are mapping to each other, should have the same input and the output nodes. Then only we can basically transfer the weights. So first we will train the system for this intent one, and then it will be used to train the system of the destination domain or target domain. So this is the basically transfer learning. So we use three domains: air travel, restaurant, and the hotel. And you can see that there are many common intents like budget, amenities, cuisine, rating. These are the common between the restaurant domain and the hotel domain. City and number of people are common between air travel domain and the restaurant domain. So there are many commonalities between the domains. And we can show that with the help of the transfer learning, there is an increase in the success rate. So when we are using the transfer learning, so the success rate rapidly increases. Okay, like intent restaurant transfer from ground transport. So here, from the ground transport, we are transferring to the restaurant. We are applying the transfer learning. So there is an increase in the success rate. So basically, what is the number of dialogues? So HRL without transfer learning is taking 4,809. Case 1 denotes the distant domain where two domains are completely different, and case 2 denotes the closed domain where there is much similarity between the domains. So for case 1, it was recording 4,809 utterances without transfer learning, and with transfer learning, we require only 3,700 utterances. And for the distant domain, there was a requirement of 7,830 utterances, and now there is a requirement of 5,000 utterances. So basically, now there is only one work. So last module, which is called the natural language generation. So till now, we are discussing about the dialogue manager. Now we will discuss about the natural language generation, which is the last module of dialogue systems. So natural language generation is responsible for generating, like translating an action to a natural language text. Like, you know, dialogue manager will pick up an action. That action has to translate it into text. So that is basically done by the natural language generation module. So we will be discussing about a particular approach where we developed a natural language generation module using persona. So, you know, user can have different aspects of the attributes. So depending on the personalization, depending on the user characteristics, we can generate the answers. So enriching any dialogue systems to exhibit consistent personas is fundamental for deriving human-like conversations. So in this particular task, we have incorporated the persona information for generating the natural language dialogues. So actions of consistent and steady personality, as these VAs are primarily trained with many dialogues from different speakers. So basically, you know, our proposed system looks like this. So there is a utterance representation. So basically there is a utterance representation which represents the utterances. Then there is a persona representation. So persona used to remember the personality of a particular user. So we are concatenating these two representations and then passing through the decoder. So this is a encoder decoder based approach. So very much similar to the machine translation. So here the encoder is encoding the utterance representation of the persona. Then it is passing through the decoder to decode the output. So these are basically, it is the methodology. And this is the hierarchical encoder decoder model. And we have the main novelty is that here there are some reinforcement learning based reward function also incorporated. So we proposed a person-aware neural reinforcement learning response generation framework that utilizes the hierarchical encoder decoder architecture tuned in accordance with the personas of the speaker. The utility of the reinforcement learning helps optimize long-term rewards in the ongoing dialogue resembling approximations that characterize a good conversation to a human mind. So basically, this is the active contribution that we incorporated the persona as well as we incorporated the RL-based rewards. So these are some results. So we have shown that with the RL-based reward, there is an improvement in the performance metrics. So in this case, there are some this perplexity or the blue scores of the performance metrics. So there is an improvement in the performance metrics with the information, with the incorporation of the RL-based reward and also with the incorporation of the persona. So these are the publications from our dialogue system. So my student Tulika Saha would be presenting the demo session. So Tulika is now a 5th year PhD student. So she is basically heavily worked in the field of dialogue systems. So she has already published 6 papers in journals. I have already talked about most of these papers. Like the first paper is on sentiment aware multimodal dialogue manager. Then the second paper is on the which I have not covered. So this is on basically tweet classification. Third is on again the sentiment based reward functions. Fourth is on basically this multi-domain, multi-intent based deep reinforcement learning. So basically we have worked heavily on the dialogue managers and the dialogue classification. These are some conference publications out of our work. So we work in the field of dialogue classification, intent detection, slot filling, dialogue manager, transfer learning of the dialogue manager, sentiment-based reward in dialogue manager, then multimodality in the dialogue manager, and also in natural language generation. These are some references. And if you have any question, you can ask me. Otherwise, I think I hope Tulika has joined. Tulika, have you joined?
Yes, ma'am. Yes, ma'am.
Yeah.
There. Yes.
Yeah. So Tulika has joined. So Tulika will show you the demo session. So if you have any question, you can ask me. So Tulika, maybe you can start the demo session.
Sure, ma'am.
You can share the screen. Yes.
Yeah, sure. Thank you, ma'am. Please let me know if my screen is visible.
Yes, yes.
Yes, visible.
Yeah. Yeah, so I'll just go ahead. Today I'll be showing a short demo on developing a deep neural network based classifier for intent detection. As you would be knowing, ma'am must have shown in the slides about intent detection, but I'll just share with you a small PPT and then a demo of, so both the presentation and demo will go hand in hand for a better understanding. If you have any doubts, you can just ask me in between as well. So, if the screen is visible, if not visible, please let me know. I'll just maximize my screen for a better viewing.
Yeah, it's visible, ma'am.
Okay, yeah. Today I plan to show a demo on deep neural network classifier for intent detection. So as you must be knowing, intent detection is basically the task of identifying user intent by the user utterances, which are basically commands or queries. It is basically a sentence classification task. For example, cheapest air, for example, if you take a sentence like cheapest airfare from Tacoma to Orlando, the the tag given to is for intent detection is airfare. That means the user wants to know the cheapest airfare from Tacoma to Orlando. Similarly, what types of aircraft does Delta fly? So the intent of the user is to know about the aircraft of a particular airline that they fly. So based on that, we'll be developing a classifier. So before that, I'll just since it's been told to me that a lot of people are beginners here over here, so I'll just give you step by step as to how do you put up a neural network together. So a very handy platform is Colab that is given by Google. So you simply to run a to develop a classifier in Colab, you simply just go, for example, go to Google Colab. You see, you just can see here Google Colab. You can write a name and you can get going. You can create a new notebook and you can just get going. So here, what you have to do, you do not have to install any kind of, packages required. Colab already has Keras, it already has TensorFlow, PyTorch, which are needed to run a deep learning classifier. So since you guys are beginners, I'll just start with Keras, because Keras is very handy when you are beginners. It gives you a better understanding of how to run a neural network classifier. Once you have a little idea of how to develop neural networks, you can then switch to TensorFlow and or PyTorch, which is now coming up, or most of the people now use, but it's little difficult when you just get going with a neural network. So when you have this, you can say a IPython notebook, which the Colab gives you. So the next task is to upload the data, right? In the Google Colab, you don't have the data. So you have to upload the data and then you get going with the code, right? So for simplicity, I've already uploaded the data. So you can simply go here and upload. For example, if you click upload, it brings you to your local desktop. So you can, you just simply click on it and you can upload your data. Okay. So to begin with, I will tell you what are the prerequisites or what things are necessary when you need to develop a deep learning classifier. First is, for example, your whatever API you are using. For example, now that I'm using Keras is already installed in the particular IPython notebook that I'm using. You can also use, like I said, PyTorch or TensorFlow. Now, given that you're using a Keras API, you need a backend, right, where your deep learning network gets compiled, and that is now mostly, initially it used to be Theano, but now it's switched to TensorFlow. All the codes are now compiled at the backend, which requires TensorFlow, but all this is already installed in the Colab IPython notebook. You don't have to do anything explicitly to run it. Okay. Next what I need to do is I need to import packages, right? Necessary packages. So Keras, why I'm saying that Keras is handy, because Keras simply gives you the packages or gives you the functions. You just simply need to call that functions and put it all together to run a deep learning classifier. You don't have to do manual coding one by one to keep your to run your neural network classifier. You just simply have to call necessary functions, compatible functions, put it all together, compile it and run it. So some of the important packages you require is, like, for example, NumPy, Pickle. From Keras, you simply have to import from keras.layers import star. This from Keras means from Keras layers you're importing everything. Similarly, from keras.models you need to import model. From Keras optimizers you need to import everything. No, you can simply also specify what you want, like for example input dense, but it's better that you import everything, so you will have everything needed. Now from Keras.preprocessing you need to import sequences. From Keras sequence, so for example, if from Keras sequence, if you import everything from Keras.preprocessing import star, you have everything in hand. So these are some of the important packages that you need to get going. Okay, so you need first, like I said, you need to import necessary packages. So you write it all down and you just simply run it. So now this part of my code is already compiled and executed. All right. Now I need to load necessary supporting functions. I will get back to these codes later when I actually call them in the code. So there are some necessary pre-processing functions that I need to execute before building a deep learning classifier. So let me just for simply compile it, and then I can show you what it does later. Now, since I have already uploaded my data set, for example, it is trained. So intent classification is basically done on a benchmark data set known as ATIS, which is basically an air travel information system. So, I have, you can see, for example, this is the, hello, is there, hello, I'm not able to listen to someone, I think, who's speaking. Sudhanshu, yeah, hello. Sudhanshu, I'm not able to hear you, Sudhanshu. Am I not audible? I don't know. I'm so sorry.
Ma'am, you're audible, but someone's mic is on, I think, by mistake.
Okay. Okay. So I will go ahead. If at all you feel that I'm not audible, just let me know in the text. Okay, in the message box. So you can see that this is my data set. All right. ATI's train data, and I have the ATI's train label. Similarly, I have the ATI's test data and the ATI's test label. So the idea is that you train a classifier on the train data, and then you test how good is your classifier on the test data, right? So for example, these are the utterances. For example, let's just say number 10. What kind of ground transportation is available in Denver? What is the corresponding label for that? 10 ground service, right? Similarly, 15, all flights to Baltimore after 6 p.m. So you go to the 15 number, you see it's the flight. Basically, the user is trying to know about the flights from Baltimore after 6 p.m. So you have set of utterances and its corresponding labels, which are gold standard labels, which are true labels. I already have this data set. So train data set comprises about 4,900 utterances, and I have the test data, which comprises about 890 utterances. Okay. So I have already uploaded this data set, as I showed you, test label, train label. So my next task is to load the data set in my session. Okay. So I specify the path where my data is, and I simply, read these data sets. So first I read my train data, train text, then the test data, followed by the train label and the test label. Okay. What I do next is for the train label, I have stripped line.strip what it, these are normal Python functions, strip what it removes any spaces or new line at the end of the string, for so that the label does not have any discrepancies, Next, my task is for the train and test also, I strip if there is any new line or new spaces after my sentence. I strip that. I could have done that here as well when I was reading it, but nonetheless. Okay, so now since you're seeing here the sentences that I'm having or the queries of the users that I'm having, all the sentences are not of equal words, right? One sentence is having maybe 10 words, other sentence having maybe 5 words. All right, so the sentences are of variable length. Okay, but since when I want to develop a deep learning classifier, what it is required that your input and output should be same. For example, if you cannot have an utterance having a 10 words and you cannot have the next sentence having 5 words, because ultimately what we are doing in a neural network classifier is matrix multiplication. So a matrix will have a fixed size, right? A row into column. You cannot have here row represents the number of utterances and the column represents number of words. So you cannot be having a matrix with the first column having 10 columns and the other one having 5. So you need to have fixed number of words in all the utterances. So what do I do is, first I find out what is the max to, in order of example, what can I also do is I can truncate my sentences, but by truncating the sentence, what will happen, there will be loss of information. So what do I do is I first find what is the maximum length present in a sentence, and I will then use some kind of strategy to equalize all the length of the sentences. All right, so in this part of the code, what I'm doing is I'm just finding out what is the maximum length of a sequence in my data set, and in both the train and test data combined. All right, so I will run this part of the code. All right, I hope this is done. Yeah. Okay, next is, so now I have the data set. I have already read the data set. I have the train label, test utterances, train utterances, and everything. What I next need to do is, now what I have right now are strings, right? Words, strings, characters. But ultimately in a neural network, all should be represented in the form of some numbers, some geometrical representation, which are basically numbers. Now my task is to try, convert this text into some kind of numbers, integers or floats, whatever. I'll go through that process. So my first task is, okay, my first task is to tokenize, that is split my utterances into words. So I am calling load create tokenizer function, which takes in my train data and returns a tokenizer. So we'll just go and see what the load create tokenizer does. And this is now where I'll get you through the code, which I said these are some supporting functions. So I come here to the load create tokenizer, right? See, the load create tokenizer is a function which is built by me. This is the code that I have developed, but it makes use of some of the functions or the APIs that are given by Keras itself. So my task is, first I'll split the sentences into words to find out what is the unique vocabulary of my entire data set. All right. So this function is it's a user defined function. But tokenizer, this is a class that is given by API. I create its object. What does this object does? It just, you can simply say it tokenizes your sentences into words, and it creates a unique vocabulary. That means a unique dictionary of unique vocabularies, simply. So you create an object of this class, you fit it on your train data, and that's it. The moment you fit it on your train data, it will create a dictionary of unique words. Okay, and you simply return this tokenizer to the main function, to the main part. Okay, so I get this tokenizer, right? Okay, now I'll show you what this tokenizer does. First, simply just let me run this so that I can print it and show it to you what it is doing simply. Okay, so for example, let me run this. So the length of my word index, since tokenizer is an object, right? You can't simply print it. You won't get anything. So there's an attribute of tokenizer word index which is actually a dictionary. So I am printing the length of this word index. That is, it is showing 889. That means what? There are 889 unique vocabulary or unique words in the train data set. All right. Now, for example, if I simply print word index, you see, you just print the entire dictionary. So for example, the word wanted has got an ID of 638. The word Washington has got an ID of 32. It's basically a dictionary, where the key is your unique vocab, and the value is its corresponding unique ID and nothing else. You need this simply to create your model, because the model ultimately needs a number and not the text. All right, so this is your index. All right. Next, since I told you, since we'll be dealing with matrices, so matrices require a fixed dimension, right, of rows and columns. But here we see that our utterances are of variable length. So what do we want to do? We want to pad our data. Like I said, if we truncate the data, there will be loss of information, right? So we want to pad the data. For example, whatever information I have, then I incorporate extra padding to make it equal to the maximum length. All right. So I call a function known as load create padded data. All right. So let me just go and tell you what this does. Load. Okay. By the way, if you have any problem, you can just interrupt me in between and you can ask me. All right. So this is the load create padded data. This is also a user defined function, but it makes use of Keras, functions in between. So what am I doing is, so it is basically calling the tokenizer, which I have already created. What I'm doing is I'm doing text to sequences. That means with the help of the tokenizer, I am replacing the text to its corresponding sequence number. And then I am padding the data with the maximum length. To view it, you can simply see, for example, you have the word index, right, which is a dictionary of unique vocab and unique ID. When you do text to sequences, what you do is, for example, if you have an utterance like, for example, flight from Bangalore to Delhi, and in your word index, the flight has been assigned an ID of 3, from has been assigned an ID of 18, Bangalore has been assigned an ID of 29, 2 has been assigned an ID of 78, and Delhi 109. This is, for example, this is just a random example. Now you want to pad the sequences. So what the text to sequences does, it replaces the text to sequence numbers. And what the padding does, for example, the maximum length of an utterance is, say, 10. So it just pads, for example, here the length is 5. So it simply adds zeros. So 10 minus 5 is 5. So 5 zeros had been added at the end or at the starting. So this is post padding and this is pre padding. By default, Keras takes pre padding, but if you want, you can specify that you want post padding. So either it can pad it at the before the real number starts, or after your real words end. So this is what happens in, if you visualize it, this is what this code does and nothing else. That means you are fitting a text to sequences and simply padding it. These are the functions which are Keras given, Keras built. You can simply call them. Yeah, please.
Actually, I have a doubt.
Yeah.
How do you find that max length? Like
Yeah. Here I have specified, right? Just a second. Here I was calculating the max length from the entire train and test data. Train and test, I have taken it in the list, and with the help of small written code, I was finding out what is the maximum sequence length. And this sequence length, I'm actually passing through this, see the load create padded data. I'm actually passing the sequence length, max length.
Okay.
I'm providing that this is the sequence length. So whatever it has minus, like the sequence length minus what it has, the extra is getting padded.
Okay, fine.
All right, yeah. And then what do you do? My next task is, now you have everything, right? You have the padded data. Now all your sentences are same. For example, now if you just let me show you what is happening. See, you have 4972. That means 4972 is the rows. That is the number of utterances in the train data. I told you I have 4972 utterances in the train data. And the column is 46. That means all the sentences are having equal length of 46. All right. Now, similarly, if you go for the test data, the same thing is going to happen, because I've already, padded the train data and the test data. See, 889, 46. 889 represents the number of utterances present in the test data, and 46 is the column. Means each sentence is represented by 46 words, which are equal, right? Okay. Next, my next task is, now whatever I have are integer values, right? 0, 1, 2, representing unique vocabs, right? But how to give it a semantic meaning? Ultimately, you want to convey the true meaning of flight to your neural network classifier, right? You want to convey the true meaning of aircraft or true meaning of cheapest and airfare to your neural network classifier. How do you do it? How do you give a true semantic meaning to your unique vocab? With the help of pre-trained word embeddings. I'm sure you must have heard about word embeddings. So this is what is word embedding? It is nothing but a geometrical representation of a word in the semantic space. For example, if you can plot a point having 300 dimensions, so that point will give you the geometrical representation of that word. So we have these kind of pre-trained embeddings available. For example, commonly used embeddings, for example, glove embedding, word to vec, fast text, which is given by Facebook, glove. I don't remember exactly who's given. Word to vec is given by Google. So these kind of word embeddings are available for usage. All right. So I make use of one of the available publicly available word embeddings, which is known as glove. Okay, glove embedding is readily available for research purposes. So, but the point is, how do you get that glove embedding in your collab notebook, right? Because glove embedding is a huge embedding, about 5 to 6 GB, because it contains embeddings of, you can say, about millions and millions of words. All right, so it is a huge file. So basically, how it looks like when you kind of, if you kind of happen to open that file, which is very difficult to open, you will see that you have a word and space, and you have a 300 dimensional representation of that word. So that 300 dimensional vector represents that word, and you similarly have that kind of millions and millions of words representation. All right, so how do you happen to get that word embedding in your collab file? Okay, so simply what can you do is just type collab pre-trained word embedding. So you see, you have this Google Colab link, pre-trained word embeddings. You simply go there. All right, let us just open. You go to the pre-trained word embedding section. So you see, to download the glove file, you have this particular command. All right, to download the word to vec, you have this particular command. Okay, you simply take this, copy this, and run it in your IPython notebook. So for simplicity, I have already done that. So I had already executed this. You can see I already have the glove embedding file over here with me. Okay, so it simply downloads the glove embedding file and brings it to your collab notebook. And this is a bash function just to copy, because it was downloaded in my main repository. I wanted it in the sample data, so I just simply copied it and nothing else. Okay, so I already have this glove embedding handy with me. Now what do I want to do? I want to get the representation of this so word index had 890 words, right? 890 unique vocab. I want the embeddings of vectors of this 890 words. How do I go about it? So what this is doing is, it is calling what? Load create embedding matrix, right? It is passing the word index, which is the dictionary of unique vocab, the length of the word index, and the length of the dimension of the embedding. So my dimension of my embedding is 300, right? So each word has a 300 dimensional vector. All right, so I'm passing these things to my function load create embedding matrix, and it is returning an embedding matrix to me. So let's just go ahead and see what is happening here. So now, like I said, like I told you, the glove embedding is a huge file. It's about 5 GB, if I can remember. So you can't really have that 5 GB kind of file in your memory all the time to run your programs. It is huge memory intensive, right? So, but what is my need? I need the representation of this 890 unique vocab, right? So I will simply extract that 890, the representation of those 890 words, and keep it in a matrix, and just go give away with that, the glove embedding file, right? So for that, what I do, I just simply read that read that file, the glove embedding file simply. Okay. When I read it, I simply split the word, in terms of spaces. The first field is the word, right? Like I told you, if you can somehow happen to open that file, you'll see that the first field is the word, and the fields are the 300 dimensional vector. So if you split it, the first field, the zero field, is the word, and the rest from 1 till the end is the word embedding. So what I do is I read it and I store it in the dictionary, all the words in a dictionary. All right. Next, what do I do is I iterate over my word index, which is actually a dictionary, right? So I have the keys are my words and the values are my index. So I iterate over my word index, and I check whether this word is available in my embedding dictionary or not. If this word is available, I get its vector, right? And I store it in the index of my embedding matrix. And if not, then I randomly initialize some values to it. You can also give zeros to it, or no, simply people say that if you have, for example, you have, say, supposing in the glove embedding you have millions and millions of words, but there might be some words which are not available. For example, some place name, some animal name might not be available, so you might not get its embedding. What do? So you give it, you can initialize it with zeros, all zeros, or you can give it some random numbers, real numbers, or simply with zeros, and whatever you have, you store it in the embedding matrix, or you can give some zeros. So to put it all together, how does it look? Let me just show you. You have the word index, right, where the key is your word and the value is your index, and the length of this word index is the unique vocab. All right, you have your reading your pre-trained embedding, and you're creating a dictionary. What does the dictionary contain? The key is your word, and the value is the vector, the 300 dimensional vector, and the length of this embedding dictionary is the length of the pre-trained embedding. How many words are present in the pre-trained embedding? That many words are available in embedding dictionary. Finally, what I'm doing in the embedding matrix, I am mapping this word to this word to get this index and its corresponding vector. So the length of my embedding matrix is unique vocab into embedding dimension. For example, if you look here, I have initialized my embedding matrix with a dimension of vocab size, comma, embedding dimension. Ultimately, I want my embedding matrix to have a row of unique vocab, that is 890, and the column of 300, that is the embedding dimension. Am I making sense, or am I clear? If you have any doubts, please say.
Yes, ma'am, it is clear.
Yeah. So let me just print and show you what my embedding matrix contains now. See, 890 cross 300. You have 890 rows representing unique vocabulary of your data set, and 300 columns, that is each word is represented using 300 column values. All right. Now, so like I said, the first task is to tokenize the words, create a dictionary of unique vocabulary, pad your train data and test data, and then create an embedding matrix of your unique vocabulary using a pre-trained embedding. Now I'll also show you, for example, X train, right? This is what you can say a NumPy array, right? Where your data is padded. Now I can go into one of its index and show you what it looks like actually. So you see, this is a NumPy array where this is a pre-padding. Like I told you, Keras by default takes pre-padding. So you have all zeros, and then after that you have 12, 47, 25, 1, 189. These are your unique vocabulary IDs. That means whatever 12 is representing, that is contained in this sentence. And in the embedding matrix for 12, I have its corresponding geometrical representation of 300 dimension. Am I clear, guys?
Yes, ma'am.
Yeah. Okay. Next, so I am done with my data. All right, so I am done with my data, like the sentences. Now I want my labels. Because till now I have done nothing for my labels. I have just, I have read them, that's it. Next, I need to create one hot encoded labels. So here we are doing a multi-class classification problem. Like given a sentence, I want to give it a label given a set of labels. Okay, so what do? I have already read my label file, right? So I iterate over my train label, all right, and I create a dictionary of unique labels, right? Here also I want to find out what is my unique label, and then assign, I want to do a one hot encoding labels out of it. So let me just run this code and show you. So here you see I am printing length label dict, right? So here it's coming 23. That means there are 23 unique labels in the train data. Why here I'm mentioning train data is because ultimately I want to train my classifier in the train data and see whether that classifier is generalizable or how good it is for the test data. Okay, so here I see that there are 23 unique labels available. Next, what I want to do, now I'll tell you in picture how it looks, what I want to do, and then I'll get into the code. Create one hot encoded labels. For example, now say supposing I have three labels, forget 23. For example, in one of the problem statements, you have three labels. Okay, you find unique labels using the dictionary. So supposing you have three. Let's just say that you have labels as X, Y, Z. So you give it a unique ID 0, 1, 2, right? We want to create a one hot encoding, right, out of it. For example, I initialize a numpy with all zeros of 3 length because I have 3 labels. For a particular utterance, if my label is Y, for its particular position, I give it a value of 1, rest of it is 0. This is called as one hot encoding. Similarly, if for a particular utterance, the label is Z, for its particular position, I am giving it a value of 1 and the rest of it is 0. This is representing my label Y in my neural network classifier. This is representing my label Z in neural network classifier. Is it clear now, guys?
Yes.
Yeah. So this is what I'm doing. Here I'm creating a unique dictionary using my trained data. Here for each of the sentences or for each of the label of trained data and test data, I am first initializing a numpy arrow of zeros of the length LBL dict, and in the position of that label, I am giving it a value of 1 and I'm appending it to my main list, Y train and Y test. So now if you want to see what my Y test contains or what my Y train contains, simply see. So Y test shape is what? 889, 23. That means for 889 utterances, I have a fixed label set 23. That means one sentence label is represented using 23 variables, out of which one is 1, right? And if you want to go on a particular position of Y test and see what it is happening, then for example, Y test 24. So you see its first position is 1. That means it belongs to a label which has the first unique ID and the rest of it is all zeros. All right. This
Hello.
is what I'm doing. So I have, yeah, please.
In the create label function,
Yeah.
what is that triple X and Y? I didn't understand that.
Oh, triple is just a temporary name, just a temporary variable. Not just to store the numpy array for.
Okay, so this is this function is being called for each and every sentence.
Yeah, for each and every sentence. Not each and every, for each and every label of the data set. For example, has 4972 labels. It is being called for every of that. Y test has about, you can say 889. It is being called for every of that. Okay. So I am done with my data. My data is ready. My labels are ready. Next, I want to focus on creating my model. So till now, whatever much use was of the Python, not very much of the Keras. You needed Keras just for tokenizing your data and padding your data simply. Now for creating the model, you make much use of Keras. So what do you do? First, in your neural network, you have input and then you have multiple layers of processing and then you have the output. All right. You can visualize. If you can visualize, I did not put it picture actually. If you can visualize, the first layer is the input. You have multiple layers of processing and then the final layer is the output, which gives you the classification labels. All right. So I have the input. Which shape is sequence length? What is sequence length? The maximum length, right? I have actually find out what is my sequence length. You can see it's showing here 46. All right. So I am putting my input layer whose shape is sequence length 46. All right. Next, after input should be my embedding layer, because ultimately the sequence length is containing what? The unique IDs of my vocab, right? But ultimately I want to represent it using the word embeddings. So corresponding to the input layer is my word embedding layer. What is the word embedding layer? For the embedding layer, I have word index, like the length of the word index, its input dimension is what? For embedding layer, I have 890 cross 300, right? So its input dimension is word index plus 1 and the output dimension is the embedding dimension. where each of these columns can actually get its weights by embedding matrix, right? The embedding layer weights should be initialized using the embedding matrix, and the input length should be the sequence length again. This is how the Keras takes in the embedding layer. You need to specify the input dimension, output dimension, where the weights of the embedding dimension, embedding layer should be is stored. It is actually stored in the embedding matrix, and the input length, which is the sequence length. All right. See, now this embedding layer is actually connected to the input layer. This is what is my embedding layer. All right, this particular line is my embedding layer, but this should be connected to my input layer, which is the first layer, which I'm getting over here, inputs. Similarly, to whatever layers we go on processing below, it should be connected to its previous layer or whatever layers, because ultimately there should not be any breakage between the layers. It should be a continuously flowing layers. All right. Next, what? I am using a convolutional network. I don't know whether you guys are aware of it or not, but a convolutional layer is used for a classification task. I'll give you a very short example of how convolution layer works. So just to put it into perspective, the convolution layer is, for example, I'm taking a convolution 1D, one-dimensional convolution layer. Number of filters are 64. The kernel size is 10. All right. Now I'll tell you what it is happening. This convolution layer is joined with the embedding layer. So you have the input layer, then you have the embedding layer, then you have the convolution layer. All right. Now to put things into perspective, I have made a very small example for you all to understand. For example, you have a sentence like Bangalore to Delhi. Obviously the sentence should be more large, but just for a simple example for you all to understand, you have a sentence Bangalore to Delhi. All right. Say supposing for example, here my filter size was 64 and my kernel size was 10, right? For a better understanding, let me tell you my filter size is say 10. No, 10 would be difficult to understand. Let's just say filter size is 32 and my kernel size is 2. What does the kernel size does? It iterates over 2 words at a time. For example, if my kernel size is 10, it will iterate over 10 words at a time. All right. So if my kernel size is 2, it will iterate over 2 words at a time. And what does a filter does? So you see Bangalore is represented using a 300 dimensional vector. 2 is represented using a 300 dimensional vector. Delhi is represented using a 300 dimensional vector. What does a filter does? You get a filter, all right? That filter is of length 2, this 2, okay, which is initialized randomly. The values of the filters are initialized randomly, and you perform a convolutional operation with the filter and your 2 words at a time, because your kernel size is 2. So what do? You do a element-wise multiplication. Convolutional operation is basically a element-wise multiplication. So what do? You have x1, which is Bangalore, into the f1. The filter size is also 2, right? So you can also say, you can say the filter sizes of this length. So x1 into f1 plus x2 into f2 will give you a value, say z1. At the next time step, you move one window ahead because your kernel size is 2. Then you slide your window. You come to 2 Delhi. Here what you do? X2 into F1, because my filter is the same. The initialization of my filter is the same. That means the value of F1 and F2 remains constant. Only my input words keeps on changing. So X2 into F1 plus X3 into F2. It gives you a value say Z2. Okay. Supposing this is now my end of the sentence, right? So you had to iterate 2 times for completing a length of 3 sentences. You get 2 values, Z1 and Z2. Since my filter size is 32, I'll repeat these 2 operations 32 times with different initialization of my filters. Right? Am I making sense? You guys understanding?
Yes.
Yeah.
Yes.
So you repeat this process 32 times because my filter size is 32 with different initialization of my filters to abstract different representation of my sentence. All right. This is what the con 1D layer is doing. Here, I have kept the filter size as 64, kernel size is 10. So I will iterate for 10 words at a time for each particular sentences. And I'll repeat the entire process 64 times because my filter size is 64. So don't think that this is happening sequentially, okay? The 64 times operation is happening parallelly, all right? That is why it makes it faster. Next is max pooling. What is max pooling doing? Now, since you have Z1, Z2, for one iteration of the filter, you have two values, right? Z1, Z2. Out of this, you are taking the max pool. That means I am taking the value which is the highest. So maybe say Z2 is the highest. So you take the Z2 value. This is representing one iteration of the filter. 64 you have. So suppose 32 you have. So you get one value out of one iteration. So if you iterate it 32 times, you get 32 values. You stack them all together, 32. Okay. In the next time step, I am in the 32 stacked values, I am again applying con 1D of 128 filters, kernel size is 10. Right? So this process is again continuing for a window size of 10, and I'm doing it for 128 times. And I'm again getting a values because again doing max pool, and I again get a set of values. And I flatten it all together to get, you can simply see a row of values. So this is what convolutional operation does. You take the element wise multiplication and you take the max pool. So it might sound a bit absurd because it's just matrix multiplication and simply multiplication, but this is how nonlinearity is introduced in these modalities to somehow make sense of it. If you visualize, then you will not understand what it is actually giving you. There's no definite definition of what it is giving you, but it is doing something and it is giving us good results. So we are just using it. That's it. Next, one of the important things is you need to give some activation to each of these layers, conv layers, activation. So ReLU is one kind of activation function, softmax, tanh. Why do we use ReLU? Because ReLU is, it maps the, basically the task of any activation function is to, map the values from one range to the other. So what does ReLU does? It actually, filters out all the negative values. For example, if for one, index of the matrix, you have a value of say minus 2.5, it will squash it to a range of 0 to positive. So example, minus 2.5 will become 0. And if you have supposing 3.5, it will remain 3.5. So it filters out all the negative values. Okay. Similarly, if you have softmax, what does softmax does? Squashes the range of values between 0 to 1. So it gives you a probabilistic values and nothing else. So you see, you have the, so like I said, I have the conv layer. This is again connected to my embedding layer. Similarly, I have the max pool layer, which is connected to my conv layer. I have the dropout layer, which is connected to the max pool layer. Similarly, you have conv1, which is connected to dropout. You have max pool 1, which is connected to conv1. Then you flatten all of it. You create an simply a row or array out of it. You have the then you have a dense layer, that is a fully connected layer of 1000 neurons, you can say. And then ultimately you have the final output layer, which should be what? With the length of the output layer should be what? The length of your labels. So LBL DAIICT is what? Contains the unique labels. So length of it is 23. So I want my output layer to have 23 neurons, because this is what my unique label IDs are. And the final activation of this layer is softmax, because ultimately I want these neurons to give me a probabilistic value. What does actually in softmax, you know what happens? For all these 23 neurons, the values added should be equal to 1. It squashes the values in that range 0 to 1, obviously, but the values of all these 23 neurons combined should be equal to 1. That means if a neuron is having higher value, that means the more chances of it to occur given a sentence. That means, for example, I'll show you. For example, the prediction is 0.2, 0.6, 0.2. The probabilistic value here is higher. That means for a particular sentence, this is the true label. I mean, the model is predicting this to be with higher probability. And 0.2 and 0.3, that means these labels are being predicted with less probability. And this label is being predicted with higher probability. So I will assign my classifier at the label as like 010, which is Y for this particular example that I'm talking about for a particular utterance. All right. And then, so you put it all these things together. See, again, the prediction one is connected to prediction. Then you have Adam. What is Adam? Adam is actually an optimizer. So I'll come to it, what is happening. Finally, to put things into perspective, model is basically the main Keras API to build the model. Here the input is basically this input and output is finally this output layer. So I'm telling my model that this is my input layer and this is my output layer, and you connect things in between which I'm giving you. Okay. And then you compile your model where your optimism is Adam, your loss is categorical cross entropy, and what do you want to monitor when you train the model is the accuracy. Okay, now let me just come one by one. What is loss? Categorical cross entropy loss. What is categorical cross entropy loss? This is nothing but softmax activation plus cross entropy loss. So I already told you what is softmax activation. It squashes the values in a range of 0 to 1, given all summation of all these values should be equal to 1. So if you add it all together, 0.6.2.2, it is equal to 1. All right. And you apply the cross entropy loss. What is the cross entropy loss? Y true log of y pred. So you take the summation, you iterate over all the label values. So here my labels are 0 to 2. Actually it should be 0 to 2, not 3. 0 1 2 y true log of y pred. So if this is my true label and this is my prediction, what do I do? 0 into log of 0.2, 0 into log of 0.2, then 1 log of 0.6, 0 log of 0.2, and you add it all together. So what is happening? Since this is 0, this is getting nullified, right? This part is getting nullified. And the only factor that is contributing to the loss is 1. So basically, I'm telling my loss to focus on this value, true prediction. I want my predicted value to be as closer to 1. If I want my predicted value to be as closer to 1, if I want this value to increase, this should go down, right? Because the summation of all this is equal to 1. If I want my predicted 0.6 to go higher, then 0.2, 0.2 needs to go down, because ultimately the summation of all this is equal to 1. Right? So in this case, this gets nullified, this gets nullified. And when you calculate all these things together, you get a loss of 0.52. This is what my categorical cross entropy loss is. So in this particular case, I get a loss of 0.52. This is what I want to minimize. That means I want to minimize my loss function, right? I want my loss to go down to 0. Okay. When you get a loss of, say, supposing a value, what does optimizer does? So if you get a loss of some value, you want to basically ensure how much of that loss should be back propagated. That means how much of this loss is affecting your higher weights in the hierarchy. That is being controlled using the optimizer, which is the Adam optimizer. There are different kinds of optimizer available, AdaGrad, RMS Prop. But for classification, it's seen that Adam works better. But for different problems, you can use and try different things. Where my learning rate is 0.01 and the decay rate is 0.3. That means the loss is 0.52, for example. How much of that loss should be backpropagated? So 0.01 into 0.52. Actually, it's not that simple. You take the first derivative of that and then you backpropagate. But just for from the technical point of view, this is what is happening. How much of the loss you're backpropagating, and decay does what? After some time step, your learning rate keeps on decreasing by 0.3. Okay. So you put all these things together and you fit the model. See, until now, everything here is a placeholder. There is no actual values assigned. Everything is a placeholder. The moment you fit the value, that means you're assigning real values to it. I am fitting my model using train data, train label. I am telling that I should run run the classifier for 4 epochs. Batch size is 64. That means at a given time, 64 of such utterances are being evaluated, and whatever loss I am getting, I am backpropagating. Then I'm doing for the next 64. Then I'm doing for the next 64 utterances. And this is my validation data. So I'm training on this data and I'm testing on this data. All right. And then you put, so example, let me just run it for a better understanding. Let me run one by one. it's saying that I have created the model, but I have not fed the model. That means the model is compiled. There is no error. All right. Now, I'm just for a simpler understanding, I'm trying to show you what the model.summary does. So if you want to know how your model is being created and everything is correct or not, you can use this command model.summary. So what is happening? You see, you have the input layer there, right? Which is 46. You have the embedding layer, which is 46, 300. Then the convolutional layer is of 64 filters. You take the max pool of it, then it becomes 2364. Then you have the dropout, it remains the same. You have the next convolution layer, which is 128 filters. So 23, 128. Then you have the max pooling. So my pool size is 2, then 11, 128. Then you flatten all of it. So that means what? You just simply multiplying 11 cross 128 together and you make it a row. Since this is like 3 dimension, right? You make it 2 dimension. That's it. And then you have a dense layer of 1000 neurons, and finally you have a dense layer of 23 neurons. So this is how the entire neural network is. All right. Now what I'll do, I'll fit the model and show you what's happening. So you fit the model, and ultimately what your model learns after the 4th epoch, I am testing it against my test data. So I'm doing model.predict. This model is what contains all the parameters and everything. I am using the predict function to actually predict my test data after the 4th epoch and store my prediction in the predicted variable. So let's just run this and show what's happening. So you see, the moment you run this, the training starts to happen. It's showing that train on 4972 samples, validate on 889 samples. So this is the first epoch of the 4th epoch. So you see the training has happened for the first epoch, and you can see the loss is 5.4644. The accuracy is 70%. The validation loss on the validation data, the validation loss is 1.3669 and the validation accuracy is 0.7323. In the second epoch, you see the loss is going down. First, my loss was 5.4. This loss is on the training data, the first loss. And the validation loss is on the validation data. That is the X test and Y test. Here, the validation loss is going down. The accuracy is going high. Similarly, the validation loss is also going down and the validation accuracy is going higher. So you see the training is completed for the 4th epoch. And ultimately, I get an accuracy on the training data 84%. And for the testing data, I get an accuracy of 80%. Okay. This is like, you obviously we need to train for a longer number of epochs just for simply running the model. This is just for the 4th epoch, and you can play around with the batches also. Like here I am my upgrade, the back propagation is happening for after every 64 utterances. You can change that as well. Next, like I told you, I have already predicted my test data using the parameters after the 4th epoch. I have everything here. So ultimately you see, this is, if you find the max of this, what will be the value? Tell me, if you find the max of this particular list, what will be the value? Hello, everyone. Can anyone tell me the max of this particular list?
0.61.
Sorry?
0.6.
Yeah, the max is 0.6. And what is the argmax of it? Argmax of this list?
0.6.
Sorry?
It will be 1.
Yeah, it will be 1. So max gives you the value which is having the highest value, right? And argmax is giving you the index having the highest value. So ultimately what I'm doing is I am assigning the label having the highest value. Here 1 is having the highest value. That means the predicted label is 1. I mean, for here 0, 1, 2, then it is 1. If my value over here would have been the highest, the predicted label would have been 2. Because for my 0, 1, 2th position, I'm getting the highest value. All right. So this is what I'm doing. From the predicted, I'm finding out what is the argmax of it. So I'm finding out basically the position. And from the Y test, I can already get the position because these are one hot encoded values. And ultimately, I want to put it all together and see how I'm getting the results. So for
Excuse
that,
me.
yeah, please.
Can you repeat why we are using the argmax?
Okay, for argmax, basically, see, ultimately we want to get which of the labels should be assigned to the given sentence, right? So
Yeah.
here my model is saying that I am predicting that with higher confidence, this should be the value. I am having higher
Yes.
confidence on this particular value. So I am finding which of the position is having the highest predicted value. So here this
Okay.
position is having the highest predicted value. So I'm assigning it the label of 1 because 0, 1, 2, this is 1.
This
Right?
010, it is because of one hot encoding.
Encoding, yes, exactly.
Yeah. Okay.
Ultimately, this is the label. X is 0, Y is 1, 2 is Z. For the one hot encoding, I'm represented it like this.
Yeah.
And ultimately from
Okay.
the softmax, I'm getting this. All right?
Okay. Thank
Yeah. Now I want to evaluate my model, right? With in terms of different matrix, like for example, accuracy, F1 score, confusion matrix, and what are the different matrix available. For that, I make use of scikit-learn. All right. So I have the predicted positions. I have the true positions. So I compare it. Okay. For that, you can see SK matrix. I'm importing different kind of packages from sklearn. I'm importing accuracy score, confusion matrix, classification report. So you can, for example, I think I put it somewhere, but I just don't know where. Okay, I'll show you how to get them all ultimately. So, okay, I've shown you here. Let me just. You can get the tutorials of all of it over here, how to use each of these, all right? So you have the sklearn matrix known as accuracy score, classification report, all right? You can just go and read how to use them actually. So I've actually made use of it. I'll show it to you. Then you can confusion matrix. You can also write the codes for it manually, but since all these things are available, you can simply just use them. So I want to find the accuracy. So I am passing the true label and the predicted label. Similarly for the classification report, true label predicted, digits 4 because I want my values to be corrected to 4 digital decimal values, decimal points, and I have the confusion matrix. So like I told you, we get the accuracy as 80%, which we were initially getting. What does a classification report gives you? It gives you a matrix, for example, precision recall F1 score. Why do we need precision recall F1 score? For example, let's just say that you have two labels, 0 and 1 present in your data set. You train a classifier and you get an accuracy of say 90%. But when you evaluate your model, you see that you get the 90% accuracy because the samples which are having 0 label, all that are predicted correctly, but the samples which are having 1 label, those all are predicted wrongly because that was less available in your data set, because all the data set is imbalanced, right? All the labels are not equally occurring in the data set. You see that 0, because of 0 predicting correctly, your accuracy has gone to 90%, but your one label, which is 1, which had about maybe 10 samples, all of which is getting predicted incorrectly. So will you say that your classifier is well trained? No, because your model classifier is not able to distinguish between those two labels, right? So accuracy is not always a good metric to identify whether your model is good or not. In that case, you need precision recall and F1 score. What is precision? Precision tells you out of the predicted labels, how many of them are correct. So for example, for the 1th, that's for example, I had 10 for 10 labels for 1. So for example, 100 of them were corrected precision for the first label 0. All of them were predicted 100, like 100 samples, all of them were predicted 0, out of which 90 belong to 0, 10 belong to 1. So your precision for 0 becomes 0, but your precision for 1 becomes, your precision for 0 becomes 0.90, but your precision for 1 becomes 0 because none of which was predicted correctly. So precision tells you out of the predicted samples, how many of it is correct, and recall tells you from the true labels, how many of it is correct, predicted correctly. So precision is how precise I am in classifying my labels, and recall tells you how much I was able to recall from the true data. And F1 score is basically the harmonic mean of precision and recall. So for each of the labels I have, you see I have the precision and the recall. So if you simply run this, you get it. So you see, you have the precision for each of the labels, the recall for each of the labels, and the F1 score for each of the labels. You see the support for each of the labels are given, which is total makes out to be 889. And ultimately, I want to have the overall precision and recall. So, scikit-learn gives you different ways of doing it: macro average, weighted average. So normally people use weighted average because supposing if one of the classes are imbalanced, so how do you manage that? So weighted. So this is the overall precision, overall recall, overall F1 score. Okay. Next, I have the confusion matrix. What does confusion matrix tells you? To have a better analysis of your classifier in the data set, you want to find out which of the labels is getting confused with which of the labels. So here, for example, if you plot indexes around here, so it will be 0 to 16, and here it will be 0 to 16. So 0, 0, that means 0 has been properly classified with 0, 6, 20 number of times. 0 was misclassified with 2, 9 number of times. So this confusion matrix gives you a better understanding of your prediction and your classifier. So this is how all of it works. Okay, so do you have any doubts? I'll just go through it again from my slides actually. So what do you do first? You import necessary packages. Then you have the necessary supporting functions, which you can simply use it from the Keras, or you can create your own user defined functions and you can call Keras functions in between. Then you load the data set. All right. After loading the data set, you tokenize your data, you create vocabulary of the data, you pad your data. You get representations of your data using the pre-trained embedding matrix. You create one hot encoded labels of your labels, and then you create the model and fit it all together. And ultimately, you have to evaluate your model. So this is how everything works. So do you have any problem, and do you want anything to be reiterated again? Please tell me.
Everything was clear, ma'am. Thank you.
Yeah. So for your assignment, I guess, I think you guys need to do an assignment as well. So for assignment, it's a very easy task. Like I told you, like I showed you for intent detection, you have to do tweet tag classification. That means given a tweet, collected from Twitter, you have to assign a label, and that label is basically understanding the communicative intention of a tutor. For example, I and you are conversing with each other. For example, I say, hi, how are you? So basically I'm greeting, and you are also telling me, hello, I'm fine, how are you? You are also greeting me. But for example, supposing I tell you, go and bring me a glass of water. So basically I'm commanding you. So understanding communicative intention of a speaker is what is meant by speech act classification. From speech act classification, if we bring that concept to dialogues, it becomes dialogue act classification. If we bring this concept in Twitter, it becomes tweet act classification. So understanding the communicative intention of a tweeter, the person who tweets is a tweeter, is known as tweet act classification. So given a tweet, you have to assign a tag among a set of tags. Okay, so what you do, ultimately you find the argmax, give from a set of labels given your x basically your tweet. So you assign a tag to it given a set of labels. For this, what do you need to do? You need to develop a deep neural network in Keras using one-dimensional convolution neural network, which I showed you, using a filter size of 32 and kernel size of 3, and a bidirectional long short-term memory network having 72 units each. I am sure ma'am has in the slide shown you a task of slot filling, right? There she must have told you that the usage of BILSTM or GRUs. So here you simply have to use one classifier using convolution neural network, one classification using BILSTM. It's very easy. You can simply, don't think that's a too difficult task. You can simply go to Keras documentation and you can see it all. Everything is there. So you can simply go and check how to implement a Keras model in using BILSTM. So you get all of it over here simply. I'm simply you can just where can I share the message actually? Nowhere to share the message. Okay, nonetheless, how do I share the message with you?
You can share in the chat.
Hi, ma'am.
Where is the chat? So this is the Keras documentation. So for convolution neural network, I have already showed you. You can simply go and see for BILSTM. It's very simple. It's more easy than convolution neural network. You simply just need a one line of integration. That's it. You don't have to do max pool or anything simply, but you have to do the same thing. Like you have to do the padding, you have to equalize everything. All these things are same. In place of con 1D, you just have to incorporate BILSTM with 72 units each. That's it. All right. Next, like I told you, you can use glove, word to wake, or fast text embedding for representing words as word vectors. I've already showed you how do you get these embeddings in Colab. Results should be reported on train test data split of 80-20%. So the data that will be shared with you is not splitted into train or test, right? So you have to split it by your own using scikit-learn. So how do you do that? You simply type that, you go to train test split. You see how what is happening. You simply call the train test split function. What do you pass? The entire data with its corresponding label. And you say that what test size you want. So here, as I mentioned, 80-20. So here it should be 0.20, your test size. And you say that random state is like after how many random states it's just a variable that is required. What it will return to you? X train, X test, Y train, Y test. So you get a like how I had ATS train test. You similarly have the same thing. So this is one thing that you have to do extra. I've just added this so that you guys will be used to doing it. Okay. So you have to use scikit-learn for splitting the data. Evaluate and compare your models. You have to compare these two models and you find out which one is working well. Evaluate and compare your models using metrics such as accuracy, F1 score, additionally also reporting overall precision, recall, and confusion matrix for the models. Scikit-learn can be used for reporting these values. And ultimately, none of the NLP application is, complete without, analysis. So you have to, find out few incorrect samples from the test set and deduce the possible reasons for its misclassification. So you see the accuracy is 80%, that there must be some misclassified utterances. So you have to deduce what could be the possible reason for its misclassification. So this is the assignment that you guys need to do, and I think you need to submit it in the Google Classroom. I think Sriparna is there to help you out in this. So if you guys have any doubts, please let me know. So I'm sure the assignment has been shared with you. I'll just this is assignment and this is the data.
Excuse me, ma'am.
Yeah. Please go ahead.
I have a doubt in the fifth question. How to select that incorrect few samples?
How to select on? You can randomly select few incorrect samples and deduce a possible reason out for it. Like you don't have to like go ahead. Like randomly you select few incorrect samples, predictably misclassified samples, and deduce what could be a possible reason for it. Because none of the NLP application is complete without a proper analysis. So just for a initial understanding of where things could go wrong, this task has been assigned to you all. So this is the data, guys. You can see there are about, if I select this row, you will be having about 7,500 tweets are there with the corresponding labels. This is the label. So this is the tweet, and then you have the label. All right. So this is the task. Please let me know if you have any other doubts.
Ma'am, if we have doubt during executing the code, so can we get your mail ID?
Yeah, you already you have my email ID. I'm just typing in the chat again so that you all can have it. So that's my email ID. You can mail me. You can ping me in Hangouts also if you want. I'm there.
Thank you, ma'am.
Yeah. So I hope you guys won't have any problem because it's not too difficult in Keras. But after you go ahead with more difficult implementations, it will be good to explore. Yeah. Thank you, Sandeep. Thank you so much. Yeah. Anything else, guys?
No, thank you, ma'am.
Oh, thank you so much, everyone. So I guess Shripad is not there. Hello, Shripad. Like,
Yeah, thanks, Sarika. And just do one thing, just share the demo notebook with me that they can also refer and use it.
Okay. So I'll share with you the link so you can
Yeah,
make it
sure.
available to
Yeah.
others.
Yeah, sure. Yeah.
Okay,
Yeah.
sure. Thank you, everyone. Thank you. Please
Yeah.
ping me in Hangout so you can mail me if you have any issues. Thank you, everyone. I'll just take a leave.
Thanks.
Thanks.
Okay, we take a 10 minutes break now and we'll meet in 10 minutes again.
Yeah, good evening. We are all back. This is Prasenjit. Thanks, Shurupendu, for the slides. So here is a plan for our Friday, coming Friday. As we mentioned in the original plan that there will be a project day, and which is Friday. So here we try to frame one capstone project kind of thing with 4 small tasks in it. And the idea is to culminate everything, if not everything, most of the things that we learned in the school for last 2 weeks, for last few days, about 10 days, and bring them together in one framework. So the task that we choose essentially is a text classification task. Text classification, you understood that by now is a very useful thing, and that has its usage in social analytics, social media analytics, in information retrieval, and many other such applications. So here is how we plan the project. So there are 4 tasks. You are supposed to train a classifier. So we try to pick up 2 classifiers or identify 2 classifiers because these 2 were kind of somewhat discussed in the school. If you remember our first talk by Professor Tathagata Bandyopadhyay, where he talked about logistic regression, and assuming that naive Bayes is something which is quite common and you all have a fair grasp in it theoretically also. So we thought to put 2 classifiers, one logistic regression and the other one is naive Bayes. Now, having said that, this is only the classification or the classifiers that we suggest you to use. You are free to use anything else of your choice if you want, but on the top of it. So if you wish, you can test some kind of, you can use BiLSTM, you can use anything you have in your mind, or support vector machine. But these 2 are you are supposed to use. Now in this pipeline, we need to represent text. So text representation is one big challenge in NLP. And we don't know really which representation works well in which scenario. So it's purely experimental also. So whether what to make or gloves or just the hot vectors, simple TF-IDF, or some more complex things, we don't know what will happen where, but yes, we will do a kind of comparison here. So task 1 says that represent text using TF-IDF and then put it into the classifier pipeline. And 2 classifiers are there. You can put a switch, logistic regression, and naive Bayes. Then task 2 is represent the same piece of text using what to vec. Task 3 is this. Task 3 and task 4 are little new kind of representation. What you can say that task 3 is basically we often remember a piece of text, an article, with the entities, named entities it is carrying. So that gives most of the information, and most of the information usually revolves around the proper nouns. The proper nouns are named entities. So it can be any geographical location, it can be any person's name, any event, an organization. So how about if we can represent a piece of text just with its named entities. So step one, get the named entities. There are plenty of such libraries available, and you get the named entities, and then you embed those named entities using Word2Vec, and then wrap it up into a single document vector. And then you consider that as a representation of that piece of text. And task 4 is you run a summarizer on the text, input text. You get a 20% summary of it. 20% is what we chose it ad hoc, but we want to see, because 20% is something which is very short after. So a small summary is a good representation of the document. How good is it? We can check by classifying the summary. And since in task 1 or in task 2, you have the whole document, so then we can compare whether the summaries are good representation of the documents or not. So these 4 tasks we plan to put 45 minutes each, a total. It should not take more than 3 hours. It will take even less, because once you set up the classifiers, and the representation schema will keep changing only. So that is the time that you will require, else it will run smoothly. And we'll be around you to help you out if any glitches are there. We'll be always with you during this process. So this is essentially a learning experience which can help you to brush up TF-IDF that was discussed in the information retrieval session, Word2Vec. There was a separate session on that. Named entities, how to identify them, and how it looks like having hands-on using the logistic regression and name-based classifier. And finally, a summarizer. So a session on summarization is planned tomorrow, where there will be a discussion on 2 types of summaries, extractive as well as abstractive. So regarding task 4, you can decide after tomorrow that which summarization technique you would like to choose. So I'll leave it to you. But there are some vanilla version of summarizers also, some fallback. But I don't want to influence you at this point. You can choose once you are done with the summarization session tomorrow. That is the final session in this school. So thus, the 4 such tasks will be there. And for evaluation, we will ask you to report the F1 score. Since you will compute F1 score, I didn't mention, but you can also report the recall and precision. The data set, you will be using the Reuters News data set, which is available in NLTK. There are other ways also. So on Friday, you can directly start using this framework. Or if you have any other suggestions, we will be around you on Friday. And these 4 tasks are something that you are supposed to complete and report the F1 score, recall, and precision. So that's one part of the story. We will be having one MCQ on Friday as well. So that will mostly cover everything. I mean, whatever has happened. I mean, we recorded all the sessions, and I think you have access to those recordings. If you want to make a quick revision to the discussions, to the sessions, you can do that. So that will kind of again help you to brush up that MCQ. Will help you to brush up what you learned in last 10 days or so. Now, at this moment, since some of the assignments are demanding using tweets, the social media, which is quite hot and important these days to work with it. We arrange a special hands-on session where Maulik will explain how to get tweets of your own choice and how to store them in locally and how to annotate them, for how to massage them to create a data set so that you can use for your any future application where you want to use social media. So over to Maulik. Maulik, could you please explain us?
Yeah, sure, sir. Thank you.
Yeah. Yep.
Okay, I am Maulik from DAICT. So let me share my screen. Okay, can someone confirm my screen is visible or not?
It's visible.
Yes, visible.
Okay. 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 So as sir said that a Twitter has a lot of potential that we can develop a lot, create a sentiment from the Twitter data. So we require the Twitter data. So what are the few steps this require to get the tweets? I will explain to you. So first you will require a basic regular Twitter account. So and on the top of it, you also have to confirm your mobile number with it. Otherwise, you are not allowed to use that Twitter data. So and then you will have to create one developer account. So if I just show you, so as I already have a regular Twitter account, so this will be a screen and it will show me that apply for a developer account. So as you can see, so as per your profession, you can choose anything like academic and then teacher, student, whatever is your profession. And once you create an account, basically they will ask that what kind of why you want to this data and what is your purpose, and they will authenticate this information, and they will give you the some credentials maybe after 2 days, 3 days, or maybe in a week. Sometimes they also ask some more details as well if they require. So once you have this all the information, you have to create what an application. That is, once you have credentials, you can create an application, and on the application, okay, someone have a okay. Okay, so once you can create an application, you can get this uh, four credential that has the consumer key, consumer secret, access token secret on the Twitter Twitter apps here, and this actually are useful to get the data. So now we have used the TUPI module that is actually useful. It's an API, so we can use these credentials to get to this Twitter data. So if you are using Jupyter, so you might have to use the install it on computer. Otherwise, on Colab it's already available. And yeah, so as you can see, the first would be the we have to enter the consumer key and secret. That is the about the consumer information. And then there is an access token that you can have generated. It will provide. So it will create you one API, as you can see. So now next thing is what particular data Twitter data provide us. Like let's say I have say username Bill Gates, and I want one max tweet, that is maximum one tweet, and this will give you the most recent tweet of him. So let's see. So I have just even this is a follow, but that is only one tweet, and I have printed all the details. Like some most important information I would like to tell you. That is first is the information that is date. Another is the full text. This is also very important. And there are some entities that are the hashtags. These are quite helpful. So you will get some keywords from the user's perspective, which are related to this particular tweets. And sometimes you also get data information about the location. This location is about what user has settled, but this doesn't mean that when user has tweeted this same is the location when the location is not necessary, but this is the location that the user must just suddenly provide. Otherwise, if like in mobile, we also sometimes they ask for the location. If we doesn't ask Twitter to this, then this is none. So we cannot get the exact location. So that's why geo and coordinate both are none. And yeah, and some two more important features regarding the tweets we can use is the retweet count and favorite count. These are actually more important. For example, some particular tweets are more important. Then these are the we can weight the tweets based on these two information, as you can see. And the last most information is the language. That is, I will also explain that how we can get the tweets in the different languages. So this is just a helper function I have created, which has these tweets, and it will extract some information like when it's created, entities and hashtag place, and it will return us a data frame. So let's give an example. For example, I want some tweets latest of 10 by ISRO. So I have used the Twitter cursor and I have provided the username and tweet mode is extended. Yes, this is actually useful. Actually, previously before 2018, I think tweets all are around 140 characters, but then they extend it. But the same not followed by the in API. So then this force mode is applied. So if you want the entire text, then you have to use this Twitter mode extended. Otherwise, you will get only 140 characters. Yeah, and this max tweet that is number of tweets you are wanted. So as you can see, I have created data frame that is helper function I have used here. I have provided the tweets and count, and I will get the data frame. As you can see, there is a date time, there is a tweet ID that is unique to each tweet, and there is a text, hashtags, if coordinate are present or not, and retweets and favorite counts. Now, next idea would be that if you want to search by some particular keywords or query rather than some particular user. So let's say I have searched about artificial intelligence and maximum 10 tweets I wanted. So I have replaced the Q as a text query and max would be the 10, and then I get the tweets like the regarding these are the tweets and hashtags and if retweets are available or not. Now it's possible that you want to work with some other languages. For example, in Hindi. So Twitter also provides that. So there are some list of their codes are available to each particular language. For example, Hindi there is HI, English AN, and even Gujarati there is a GU. And let's say your query is co-vaccine, and who want their result type, like for example recent, there also possible you can want popular tweet rather than recent tweets. So this all is possible, and max again 10 I will. So as you can see, I have provided this information to Twitter web module, and I have just printed top 5. So you, as you can see, I will get this tweets from as in Hindi. I will also like, give you an example demo on Gujarati. So as you can see, the all the tweets have come in the Gujarati. So we have tweeted. So these are the some recent tweets on Covaxin. So yeah, but this Twitter actually API has some limitation that it will only allow you to get the tweet from last 7 days, and there is some like you can not accept more than 18,000 tweets per 15 minute of window. And even for some particular user, let's say Bill Gates, I cannot accept 3200 more than 3200 user tweets from me. So yeah, and these are the some references actually I have given. So you can also access the more number of parameters, like if you want to like more complex queries, more different languages, or maybe some time regarding between last 2 days, last 3 days, so you can use. So these are the available. So yeah, so that's all from my side. If you have some doubts, then you can ask me.
Sir,
Yes.
in the tweets in particular language,
Yes.
so the original tweets in English are translated into the particular language. Is that the case?
No. No, someone particular has tweeted in the Gujarati, and their tweets are actually given by here.
Okay, fine.
Okay. Yeah. It's not translation. Yeah. And even, yeah, you also provide some coordinates from geolocation. So you get some particular tweets from that particular location if the user provides users are from that particular area provides their location. So it's a different case study, but you can try it. So any more doubt? Okay, then I will transfer to Surupendu for the uh, okay. So Surupendu, are you there? Hello, am I audible?
Yes, sir.
Yes, sir.
So, okay, so if no one has the doubt, then we can actually close this session, and I will share this uh, Python notebook. So maybe you can in future you can use this. So if you want to download some particular tweets and do some research. So yeah, okay.
Thank you.
Maulik, if you are done, then we can close the session for today if there
Yeah,
are
yeah,
no more doubts.
I am done. Yeah.
Okay, so then we will close the session for today, and tomorrow the session starts at 3 p.m. again, and it will be on summarization by Dr. Parth Mehta. Thank you, everyone.
Thank you.